Can you guys see my screen?
Yes, sir. It is visible.
Okay.
Yes, sir, it's visible.
Okay. So now let's try to. All of you have see in the textbook we study about the small signal model. Okay, and we say that the output impedance is obtained by applying a test voltage at the output and measuring the current through the device. So now most of you let us devise an experiment simulation to measure the output impedance. Okay, so can you guys see the schematic right now?
Yes.
Yes, sir. You can maximize, sir.
Yes, sir.
Yes, so you guys can see this, right? So now let us say I want to
Sir,
measure
please
what.
make it full screen, sir, if possible.
Okay, is it okay?
Yes,
Yes,
sir.
sir.
Actually, I want to put a few things. That's why I don't want to make it full screen because there will be multiple windows. So that's why I'm not making it full screen.
No problem, sir. No problem.
Okay. So now, please I want all of you, if you have any doubts, you ask questions. Okay. Now, the goal is what is the output impedance of this device? Okay. Now, how do you measure it? We say that it is RO, but we should have a means to measure it, because how did that RO come in, right? So first of all, in order to make sure that this transistor, so let me show you the property of this transistor first. So this is a 10 micron device. Now here I want to highlight a few aspects. So if I see the parameters of the transistor, I'm sure you can see this. First of all, I've chosen an NMOS. Now there is something called finger. So there is something called finger, there is length of the transistor, there is total width, and there is something called a multiplier. Okay, so I will explain this as I go along. So right now I have devised, and the number of fingers are also there. Right now it is a one finger device, okay, one multiplier device. Each finger is 10 microns. So suppose I make this 2, right? Then you can see that this is a 2-finger device. The total width stays at 10 and this finger width is 5, so because 5 times 2 is 10. Okay, so now I can, if I make the finger width 10, then you can see that this automatically becomes 20. Okay, can you guys see this thing clearly, all of you?
Yes. Yes.
Okay. Okay. So now, if I want to achieve same 20 micron device with each finger 10, and I want to have one finger device, then I can also achieve that with 2 multipliers, each of like this. So I can have 2 multipliers, each is 10 micron wide. So 10 times 2 is 20. So I can realize it in various ways. Now, whether to go for fingers or whether to go for multipliers, that is decided based on the layout. So once I go from here, I move on to the layout and we will try to understand that. Okay. So right now I have chosen a device of 10 micron single finger device, 10 micron of channel length 180 nano. Right now, I want to measure what is the output impedance. Okay. Now, in order to measure the output impedance, okay, what do? We have to apply a test voltage at the output, an AC voltage. I have to draw the small signal model in the textbook. If I tell you find output impedance, what will you do? You will apply a voltage at the output. AC, you will draw the small signal model of the transistor, apply a voltage at the output, and measure the current flowing through that voltage source. Now, in simulation, how do we do it? And so basically, we first have to make sure the transistor is in saturation. So basically, what I have done is I have applied a drain source voltage VDS here, okay, and applied a gate voltage called VG, okay, and I've used a big inductor here. Now, what does the inductor do? I have purposefully done this to measure the RO. This inductor is a big one, so it acts as a short circuit for DC. That means the DC voltage here is going to be equal to whatever is the voltage here, okay, and but it acts as an AC open circuit, means the impedance here seen this thing. So that means the transistor current, AC current, would not flow through this inductor. And in order to make sure that I am applying a test voltage without altering the voltage here, so I'll apply an AC voltage source here. You can see that this is a 0 volt, an AC voltage source. I'll apply through a capacitor and I'll make a huge capacitor. What does the capacitor do? Large capacitor, 1 kilofarad. Physically, these are unrealizable. Keep in mind, we cannot realize these. These are just for measuring this. Okay. So what will I do? I'm going to use this thing, apply a test voltage, AC voltage, sweep the frequency and find out what is the current flowing through this capacitor. The amount of current flowing through this capacitor, divide, and keep in mind the current flowing through the capacitor is going to be an AC current. That current divided by the AC voltage is the resistor, inverse of the resistance, or the output impedance, inverse of the output impedance of this one. So, but I would not divide it by the voltage because I have already set the voltage to 1. So its voltage is already set to 1, AC magnitude is set to 1. So I don't need to divide. I just find this current and that is it. Okay. So I hope this setup is clear and I hope you understand the reason why I have chosen this as 1 mega Henry and why I have chosen this as 1 kilofarad. Okay. Next thing, when the device guy is measuring this, he does not do this. This is how a circuit designer is going to find out what is the transconductance of a device. Okay. What is the effective transconductance? What is the output impedance of a device? A circuit designer does these experiments in the lab to find this out. You can do this in the lab also. There is nothing stopping you from doing this in the lab as well. Okay. This is how a circuit designer finds. A device designer finds by measuring the IDVDS and capacitance characteristics, CV characteristics, IV characteristics. That's what the device, and when the foundry, TSMC or UMC or anybody provides you the model, they do not do this. They will generate the model used by measuring the IV characteristic and CV characteristic. Okay. So now let us go into the simulation. So I'll open the simulation bench. Okay. So I will load the state. Okay. Which I have already saved. And I will tell you what is there in the state. Yes. Yes, please go ahead. Any questions? All the attendees, are you if you have any question answer, please pause because I purposely want this to be very, very interactive. Okay, so there is a on the chat. There is a question from.
Hello.
Yes.
Am I audible?
Yes, you are audible. Yes.
Sir, can you please repeat the part where you can formulated the device sizes and you have set the specified finger width value. So can you just repeat that part?
So okay, so okay. So when we are designing any amplifier or anything, right? And suppose to carry a certain amount of current, I need a certain W of the transistor. Okay. Now let us say that W is, let's say, 100 microns. So you have various ways of realizing that 100 microns. Okay. So since you have asked this, I have to now go to the layout mode to show that what is the various launch. So I just want to tell you that I still do the old-fashioned way layout and schematic, because when I learned cadence, it was way back in year 2000, 20 years back. And in the industry, when I use those cadence, I use those. In the last 5 years, cadence has improved significantly. So there are few features that, for example, they have layout XL, layout GXL and all. I am not yet familiar with those. They are much more powerful. But I still do it the old-fashioned way, and I'm comfortable with it, and my speed is not that slow when I'm doing schematic layout and all. But when you guys will be starting and all, I would suggest that you please start with layout XL, layout GXL and all, because these are much more advanced. Okay.
So actually, initially, when I have started with the layout and the template, I have used the layout XL part.
Yeah. So unfortunately, a layout XL came in the year 2011-12. By that time, I had already left my industry. Okay. So I never really had to use layout XL, because in academia, designs are small. Okay. So that's why I still do not use layout XL, but my students are using layout XL. Okay. But I can do design still in layout, regular layout. But I would recommend that you please switch to layout Excel. And for that, there are small tutorials available online. They are not big deal. They are just little more powerful. That's all. Okay. Now, let me instantiate a transistor. I will show you various flavor, same size transistor, but in various. Okay. So, okay. So let's say I want to realize a 10 micron device. Okay, let's make it a 100 micron device. Okay, so that every aspect will get clear. Okay. Now I have built a 100 micron device. So this is a big 100 micron NMOS. Okay, I can realize this 100 micron NMOS in this manner. This is flavor 1. Okay, the second flavor is going to be, I'm going to modify that properties. Okay, so what I'm going to do is I can make it every 10 microns. Okay, but I'll make it 10 fingers. Okay, so that is also a 100 micron device. This is also a 100 micron device. You can see this blues are the gates. So this is also a 100 micron device. What is the other way of realizing that same 100 micron device? And I copy this. So I can copy it like this. Number of rows, I'll make it 9. Okay. So these are some shortcuts that you will eventually, once you start using the tool, you will become. So grid size is not proper. I don't know why it did not instantiate. Oh, it did it in this manner. Okay, that is good. Okay. So now you can see that what I have done is I have realized the same 100 micron device. This is one flavor, this is flavor 2, and this is flavor 3. Okay, what is flavor 3? Flavor 3 is I have done 2 fingers, okay, and 5 of them in parallel. Okay, so it is doing the same function. It is doing the exact same function, but which one is more optimal? Now you can clearly see that if I do it with the flavor 1, the gate resistance is going to be bad. Okay, gate resistance is, so your circuit will be dominated by gate resistance at this point. Okay. Secondly, here the power, the current will all flow through this one gate. So you have to have a very thick wire because a 100 micron device can carry a huge amount of current. That means the wire, for example, if I have to deliver using, let's say, metal 2, let's see, Me2. Okay. So if I have to deliver using metal 2, I have to probably use a 20 micron wide metal 2 to deliver the amount of current that I need to deliver. Okay, but in this case, I can deliver the current with a much thinner metal. for example, with 5 micron thinner metal, and I can deliver the same amount of current. Okay. Now here the current is uniform because I'll have much more gears and all. That will also define. So there is something called electromigration that you have to worry about in high performance design. And electromigration have to be taken care of properly in terms of the current density, and also those come later. I don't think I can get into that at this point. It will be difficult. But the only way to do that is getting into a design. Unless you design it, it will never, those aspects won't ever be learned. And that's how all my students learn. They work on a design, they tape it out, and when they go through that whole flow, they learn the whole thing. So now similarly, when I have this, I can have multiple lines on top, and I can deliver this current properly. So here you can see that I have very small gate resistance. Okay, and I can connect the poly in a much more efficient manner. Okay, you can see that I can connect it in a much more efficient manner. Okay, but here one poly contact is going to connect it. You cannot put more than one poly contact. It won't help you. It is going through the gate resistance. So this is useless. So so now it all depends on how the layout, how you want to do it, what is the current carrying capacity and all. So to bring in all those concepts together, it is very difficult in this class. But there are the same transistor width can be realized in different manner. Does it clarify your my thing? So that is why in this feature they give you this option of fingers, multipliers, and this thing. So let me tell you. So this transistor is actually one finger, one multiplier, and 100 micron wide. Which one did I choose? Sorry, if I choose this one, yeah. So this is 100 micron, one finger and all. Keep in mind, in layout, there is no concept of multiplier. You just put them, multiple of them. Here, this is same 100 micron realized with 10 fingers. Okay. Now here, this is same 100 microns realized with each 2-finger devices, which is 20 microns over here, and 5 of them in parallel. That gives you the same 100 microns. Does it clarify? Does it answer your question?
Yeah, yes, sir. Now I understood. Thank you.
Okay. Okay. So now having discussed that, now let's get into this. So now what we'll do is we will do let's see this. We will do a few simulations here. So I have set the VDS as 1.8 volts here, and VG as 400 millivolts over here, gate voltage. And then I'm going to do a DC simulation, and I'm going to do an AC simulation. AC simulation, I would recommend that please note the settings. Your start and stop frequencies should be appropriately defined. Okay. What is the appropriate depends on the bandwidth of your circuit. So please define it. Usually, I would prefer that you go logarithmic here, and you should use 40 points.
Excuse me.
Yes, yes.
Yes, actually, I am not connected for at least 5 minutes. I don't know. Like, please, if you can briefly say that what you are saying about how to find out the output impedance of a
Output impedance of the
that
transistor.
amplifier.
Yes, output impedance of the transistor. Then we'll get into the output impedance of the amplifier. Okay, so we in the textbook we see the output impedance of a transistor is RO. Now let's try to find that, cook up that experiment, because how do we do? We do the small signal model, apply a test voltage at the output, and measure the current flowing through the test voltage. That is the definition of RO. We'll exactly do the same thing. Now this inductor and this capacitor are there. Inductor blocks the AC, capacitor blocks the DC. So why do we have this capacitor? Because I connected this to ground. DC voltage here is ground, because I have applied a test voltage. So I cannot disturb the DC point here. Without disturbing this DC point, how do I apply an AC signal? That means I have to apply through a capacitor. Now I'll do an AC simulation. AC simulation settings, you should use logarithmic, and typically I use 40 points per decade. Now don't use number of steps, use 40 points per decade. Okay, that is it. So now let us run this simulation. Okay, so I will look at this plot later on, but before that, so let me annotate. You can do the results, annotate DC operating point, and results, annotate DC node voltages. So as I said, I had applied 400 millivolts here. I had applied 1.8 volt. Inductor is an DC short, so you get 1.8 volt at the drain. This makes sure that this is in saturation. Okay. Then I apply an AC voltage source here, and I try to measure this current, and which is saved here. You can see that the current flowing through this transistor is saved over here. Now, how do I plot the output impedance? So I go to calculator. So all of you should be familiar with this calculator. I save the IF. So there are various buttons here. VT stands for the transient voltage. T stands for transient. V stands for voltage. VF, voltage as a function of frequency. F is frequency. VDC, voltage at DC. VS is the swept voltage when you're sweeping it. Okay. IT is the transient current. Okay. IF is the frequency, how the current varies with frequency, that is for AC simulation. IDC is the DC current. IS is the sweeping current when you sweep some value. Okay. I don't exactly know what is OS, but OP is the operating point. Then VAR is the variable, and there are other things which these are for RF and all those things. I rarely use them. SP is the S parameter, Z is the Z parameter, YP is the Y parameter. VSWR is the voltage standing wave ratio. Then this HPGD data and ZM, I don't know at this point. Okay. Now what I will do is I need to find the output resistance, output impedance of the transistor. What is the output impedance? Is the voltage, AC voltage divided by the AC current flowing through that voltage source. AC current flowing through this voltage source is the current flowing through this capacitor, which is saved over here. So AC voltage that I'm applying is 1. Keep in mind I've given 1. Okay. So therefore, if I go back to the calculator, okay, then you can see that 1 divided by the 1 is the voltage divided by the current flowing through that capacitor, IF, because it's a frequency dependent. I'm plot that, and when I plot it, I will get this value. Okay. So now what are these happening? These are all numerical inaccuracies. You can ignore them for the time being. These happen sometimes if we don't, because I did 40 points per decade, so it does some this thing. But if I sweep much more finely, I think we'll get a smoother curve here. So you can ignore this. This is the resistance, output impedance at, let's say, 100 kilohertz. Okay. So the output impedance is maintained at this value. So it is, you can see that it is roughly 116 kilo ohms. Okay. Now let us find out what is the output impedance that the DC operating point gives. Tools, results, print, DC operating point. Okay. And I click on this transistor. This tells me all the operating points of the transistor. It tells you what is the body bulk potential capacitance, body bulk drain capacitance. I don't know what this one is. Bulk gate capacitance, bulk substrate capacitance. I don't know what this is. Drain bulk, drain capacitance, drain gate capacitance, drain source capacitance, gate bulk capacitance, gate drain capacitance, gate capacitance. All these things are given. There are a lot more parameters because these models are much more complex. So let us see what is the drain current. ID is 12.13 microamp, and you see that it is 12.13 microamp here, right? Now what is the output impedance? Output impedance is given by RO. What do you see here? 115.9 kilo ohms, and that's exactly what we got from our simulation also, 115.9 kilo ohms. So this is how. Now let us see how will I find the, if I cascode this. Now let's see, by cascoding, what will be the output impedance. So please, all of you take out a pen and paper, and I will modify this circuitry in front of you, and we will measure the cascode impedance. Okay. So I am stacking the voltage source at this point, okay, so that this voltage becomes, I label this as VCASC. Okay, so am I clear with this schematic right now, all of you?
Yes. Yes.
Yes. Okay, so now what I'll do is again I'll rerun this simulation. And let's see, gate voltage is 900, this is there 900. So obviously this is also in saturation, this is also in saturation. Okay. Okay, so now I did not plot the R out. Now I would ask all of you, what will be the output impedance of this one? It will be roughly equal to the GM of this device, RO of this device, and RO of this product of these, right? So let's note down the thing. So results, print, DC operating point, we get the values. So please note down the GM. GM is 102.2 micro. Please write it down. And R out is 286 kilo ohms. Okay, so please write that down. So GM is 102.2 micro, R out is 286 kilo ohms. Let's find what is the R out of this. R out of this is 253.4 kilo ohms. Okay, 253.4 kilo ohms. Please note this down. So what is the effective output impedance? So it is going to be 253 kilo ohms times whatever was the this one here.
Okay, Prem, I have joined. There is a problem in connection. Okay.
286 kilo ohms times GM of that, which is 102 micro. Okay, so all of you can please type on the chat what is the R out that you are getting, and let us see if the simulation is also giving the same R out. I would request all of you to multiply that and obtain the resultant. So it is comes to 7.4 mega ohms roughly. Okay, that is what my calculation shows. No, sorry. 7.4 mega ohms. Yes, that is what my calculation shows. So please check that, and let us see what comes out here from the simulation. It comes out as 8.8 mega ohms. Now, what is the difference between why is this 8.8 versus why is it 7. That is an approximate thing, right? GM RO square is an approximate thing. So if you write down the exact expression for the output impedance, you will get 808.8 mega ohms. Okay, am I clear?
Yes.
Attendees, any question? Okay, if you don't have a question, this is my question to all of you. Why does the R out show this rising characteristic here? Now, it was not showing the rising characteristic in the previous case when it was not cascading. Why does it show this falling like this? That is my question. So please take a note of it. You draw the profile, ignore these jumps. Okay, these jumps will be fixed by running accurate simulations, which I have not done because I wanted to show it this thing. Why does in the previous case, the R out started off like this and then it went down. In the new case, I am seeing the R out going like this and coming down like this. Now, as a circuit designer, now you need an intuition. Now, how do I fix this? Okay, so let me show you how I'll fix it right now.
So by the frequency to
I fixed it, right? It became a straight line, right? So, you have to now reason why, what was happening. Now I changed this to 1 gigahenry. When I changed this to 1 gigahenry, why did it fix it? Why is it flat? And then when I made it 1 megahenry, it was not like that. Okay, so it was. So now if I rerun this now, you will see that you will see the other profile. You see this? So here now, why is this happening? Because the current, because the impedance has increased so much, this
Yes.
this capacity, this impedance is much smaller, is comparable to this at that point. So there will be a current division that is happening. So I should ideally be measuring the current coming out of the transistor, right? Because that is what contributes to the output impedance. Okay, how much is the current changing as I am wiggling this voltage over here? Okay, so this is how you measure the output impedance. Now, why am I
So the
showing this?
output, while I am measuring the output impedance, then I have to note down that this part, the inductive part, should not be loaded with this kind of order of the
Right,
output.
right, right, right. So that these inductors are for simulation only, so that they block the AC
Yes,
and
yes.
pass the DC, and this capacitor is going to block the DC and pass the AC, and that's what you do exactly in the small signal model when you're doing. Now, why am I showing this? Because whenever you start designing anything, you should have an idea what kind of impedance do the transistors offer. If you, that is called the on your fingertips, you should know the transistor characteristics. Okay, so now this is how you get the R out. What else do we need? We need the GM, right? So now there is another setup. I'll show that setup right now. So any attendees, any question? Do you want
Yes,
me to take note down
yes.
this schematic and note down the test bench parameters? If there are any doubts, please note it down, because you should have this in your system so that you can find out, okay, how good is a transistor? Because I don't start designing. When I got the 28 nanometer PDK, I did this sanity check first, because I need to know, okay, what can I achieve with this technology? So I need to know what is it. For example, if you are building anything, you need to know the quality of the material. So these simulations will tell you the quality of the technology. Okay, so please note this schematic down. This is the test setup for measuring the output impedance. Next, I'll show you the test setup to measure the transconductance. Because once I know GM and R out, that's all I need. But besides that, I need to know FT, and also I need to know the capacitance characteristic. Okay, so that the maximum frequency at which I can operate can also be done. Okay,
Yes.
so let me move on to the GM. If any questions from the attendees, you can type on the chat. You can unmute
So
your
actually,
microphone.
from this, can we have that the frequency, the bandwidth that the amplifier that is
Yeah, that will come from the AC simulation.
yes.
That will that when we go to the op-amp design, we'll get into that and we'll get the bandwidth and everything.
Yes.
Attendees, any question? So one small request to all the attendees. I think all attendees are also
So
faculty,
in
right?
that case, when this amplifier is connected with the load, yes,
Right.
and if his load is like the dynamic kind of load, which is like tuned with some frequencies. So in that case, can we conclude with that this amplifier will be used for the up to this frequency or this frequency, because
Yes,
out,
yes.
yes.
That from the AC simulation, it will give you the bandwidth. Yes, there is a hand being raised by Soumya Sengupta, I guess. Yes, any questions? So all the attendees, do you have
Hello?
cadence in your?
Yes, Soumya Sen Gupta, you can ask the question by unmuting yourself. Soumya Sen Gupta, if you have any questions, you can ask by unmuting your mic.
one more small suggestion. I do all the attendees. They are all faculty in college, so they have cadence access in their respective universities.
Yes, actually we are going to purchase, but till now we have no cadence.
Oh, I see. I see. So, okay. So Soumya is, you can type on the chat if that is what our question answer is there.
Yeah, if I have any question, I'll
Okay.
inform.
Okay.
Yeah.
So, okay. So then I will close this setup. Okay. So next I will go on to the GM measurement. Again, the same setup. Similar setup, but I don't have a voltage source here. GM is what? Short circuit current gain, right? So I'll measure the current flowing through this capacitor and divide it by the voltage, AC voltage. But I've set the AC voltage at 1. Okay. So same transistor here. I've taken a 1 micron device, a transistor. Okay. So now I'll open the simulation setup. Okay. So what will be the GM of this? It will be the current flowing through this capacitor divided by this voltage. Since the voltage is equal to 1, I can just plot this current, and that is the actual GM AC current. Okay. So I open the test bench. Okay. So same kind of setup. So now I'm going to do this, and you can see the GM is roughly 29.51 micro. This is what your simulation gives you. I don't know if you can see this. You can see that it is 29.51, right? So let us do results, print, PC operating point, and get this value. And the GM is given over here, 29.52 micro. Okay. So this is the GM of the transistor. Okay. Because and then my next question is, why does this go up? Why does the GM goes up as I increase the frequency? So in other words, if I go to, let's say, 10 gig or 100 gig, then you will see that
Not transform.
it goes up, right? It keeps on going up. Now, why does the transconductance increase, GM increase, based on our measurement setup? Why does it increase when, so keep in mind the GM is nothing but I use the calculator and plotted the current flowing through the capacitor divided by the voltage and the gain.
Actually, the impedance the capacitor is giving with the frequency, the capacitor is almost like a short.
Right, right. So but I'm measuring the current flowing through this capacitor, right? I'm measuring the current flowing through this capacitor, and because that is what we will do actually in the lab. So I'll measure this AC current. So this current divided by this voltage is the actual GM of the device. Now we are seeing that as the frequency increases, okay, the current is keeping on increasing.
Yes. Hello.
Yes, yes. So
Yes.
this is a thing that I want all of you to think about, and all the attendees, you can shoot me an email if you have an answer later on after this. Okay. So we have got this. Now let us see if I degenerate this. Okay. I'll put a resistor of 100.
It is the impedance, and the current is flowing through this path, through this amplifier. Okay. So
Yes.
yes, so the shorting path is through this capacitance, And is it, as it is the inverse of the impedance, then it is showing that it is increasing, no?
Yes.
The current.
Now, basically, what is happening is that previously at low frequency, this inductor acts as a short also.
Yes,
Very
dominating
shallow.
part will be on.
Some part
Yes,
will be
yes.
going through here.
Yes,
So
yes.
we are measuring a little bit less.
Yes,
So
and
is
that
why.
you have already cut it due to by increasing the inductor frequency,
Right.
so that it will all the current will flow through this.
Yes.
That is okay.
So now I put a resistor here. So what should be the transconductance of this device? So I think there is hardly any drop on this one. So I will make it 1001 kilo ohm. Okay, so that our GM drops significantly. The regenerated is GM divided by 1 plus GMR RO. Okay, so GMR. Okay, so that will be the overall transconductance of this device. Okay, so now you see that there is actually there is very little drop here. So I have to really put 10K so that you can see some degradation in the GM. Okay, so now you see that the GM of this device has come down to 42 micro. As because it has not come down actually because I made this 500 milli. So let me bring this back to 400 milli, so it will drop further. So before it was 29, now it has become 19 micro. Okay, why did it become 19 micro? Because now the transconductance of this device is GM of this divided by 1 plus GM times R of this. So you can try it out. Let's see what is the GM of this. So GM of this is 23 micro. So 24 micro divided by 1 plus 24 micro times this is 10 kilo ohms. 24 micro times 10 kilo ohms, you will see that you will get roughly 19 micro. And exactly that is what you do in the small signal analysis. So I want you to have this test bench and the other test bench for the output impedance. And always any technology is given to you, you should be able to do this experiment. And in fact, I do this when I teach analog design for the undergrads. I show them this actually in the lab. I have a small equipment, I take a thing and I show them this measurement and they can actually understand what is the meaning of AC short, what is an AC open, AC short and all those things, what is small signal model. So with this, I think
which instrument you are using for that?
I'm using a Digilent analog discovery kit. So I'll put it in the chat. Digilent analog discovery kit along with a few transistors and a breadboard. I take this to the class and show them this. The same experiment what I'm showing in simulation, I do it in front of them on using the components, TN transistors.
I think that actually help you in finding current, and if you can provide IV source measuring unit, that can also be able to do.
Yes, but that will be bulky. Here, this analog Digilent analog discovery kit is like 7,000, 8,000 rupees.
Only?
And yes, this is very cheap.
Okay.
Students can buy it for 7,000. For students, it's very cheap. For us, it is I think 15,000. But for students, it will be very cheap.
It will be from Digilent.
Digilent website is there. You can buy it from DigiKey also. DigiKey.in. You can get the same equipment.
This is that voltage and current and components are there.
No, this is a module that can act as a voltage source and a
current source, both, and
not as a current source. It can act only as a voltage source, but it can give sine wave, square wave, all kinds of waves. So I use a sine wave and use capacitors because when I'm applying an AC source here, I'm using a sine wave in a way, small signal sine wave.
Okay. So transient analysis and everything can be done, and the sweeping can be done, everything.
Everything can be done. Uh, Attendees, any questions on this?
Please ask questions if you have any, Mihir.
So all the attendees, I would request that analog design, by reading the textbook, it is not going to, it won't lead to any kind of design thing. So people have to be hands-on, and you have to learn the tools, all of you. So please spend the time to learn the tools and all. I still do the design myself, and every tape out and every chip design, the top level integration and all, I still do it. For example, the chip that you saw yesterday, I showed you the full top level chip, full top level integration. I did 50% of that, and then I showed certain things that other people do. At this time, I'm not able to do full thing because my hands are not in proper shape. I have carpal tunnel. So, but I would suggest that unless that the best way to learn analog design is by doing it. Just like the best way to learn swimming is to go into the water and get drowned once. So by taking a swimming
Yes.
class, it won't help. So all of you, I would suggest that try to procure Cadence. Cadence is available very cheap. Cadence is also very liberal in terms of giving it to academic institutions. Mentor also has a corresponding tool called Pyxis.
Mental graphics.
Mentor Graphics has a tool called Pyxis. I've typed in the chat. So you can use that tool, that is even cheaper than Cadence, and it has similar interface as Cadence. I'm not promoting Cadence or Mentor Graphics. I'm saying that by reading the textbook and drawing small signal model, designs cannot be done. So unless you dabble with it, things won't happen. Okay. So now I will go into the design of an op-amp. Okay. Should we take a few minutes break? And if there are any questions, we can take those questions also.
Yes, 5 minutes you can take.
Attendees, any question?
Actually, in the previous days, we used to do the hardware design. Not in that at that time there was no simulation type of thing.
Right.
So
right,
what
right.
we have done, that we have done by our own the IC op-amp for solving differential equations. Say
Right.
solving linear equation. We have designed that kind of thing.
Right.
Okay. One stage amplifier, two stage integrator, differentiator, power supply regulated circuits, and the amplifier, one stage, two stage, multivibrators. These we have designed it by hand, and we start with the design maybe from gain, and which transistor to be chosen, that we have to set out. That yes, this transistor to be, we can choose this. Finding beta, their parameter, that others toward like ICVC, and what should be the gain and the voltage. By seeing this, we have to choose at which transistor
Hello.
will be going. Yes.
Hello.
And
Yeah,
now we
actually,
have
yes.
Yes, Shomu, you can ask.
Yes. No, actually, I just want to say that I request ma'am to just actually set up the Cadence software in our university, so that we can just practice whatever we are being taught
Yes,
from
actually,
in the lecture.
yes, we are trying our level best,
Akshay has
because we
also
have given
mentioned this
the
website, the Digiland website.
So Digilite
Very happy.
website, I'll show you which component I use.
Yes.
So I think you can see my screen, right?
We have given the proposal, and it has been under procurement stage. But the thing is, COVID is there, so you have missed already 6-8 months.
Yeah, actually,
Otherwise,
I have practiced in the Cadence
So
through
this is the
training.
kit. This is the kit.
Okay.
yes, it's very good.
So this kit acts as an oscilloscope, as a signal generator, voltage source, logic analyzer, everything. And I do a lot of low frequency measurements with this. I have this at home. One of this, I bought it on my this thing.
Yes.
And I do a lot of experiments on my own at home. I just sit on the computer and do this. And
Yes.
now there's COVID time. My students are all over the place. So I tell them I have set up a desktop here. Desktop has this Agilent Discovery Kit connected. Screen is there. They connect. I just make the connections on the board. They do the measurement and note down the results. So you can be anywhere in the world, and still experiments can be done.
Yes.
Okay, so I
So
have
we
this setup
mastered
plan.
this. Yes, this can be done because it is very cheap in comparison to that. And
Right.
cadence,
No,
even the
Analog Devices also has come up with another board similar to this. I don't know the cost. I bought this because this is the first one that came out way back in 2013. I bought it at that time, and I'm still using it. I am a big fan of this. But Analog Devices and Texas Instruments have also similar stuff. They might be cheaper. I don't know. So these are all available. These you can take it to the class in your pocket and start the experiment. And they give
Yes.
you along with the components. They give you a bunch of components. You can see that they give you here. If you see, all the components are given here: capacitor, transistors, everything.
all are standard standard
And they give
components.
you a breadboard also. You can see that there is a breadboard
Okay.
here. So you can see that breadboard is there. So it comes with it. I usually take it to my analog class, theory class, and show them this thing because they find it hard to understand what is an AC short and all those things.
Okay, it's very good.
So my recommendation is, another thing is that the best way to learn this analog design is by doing this. And I tell first, when my PhD student joins, I give them a set of assignments. We're doing this measurement of GM, measurement of RO, measurement of FT, measurement of capacitance, then all those linearity measurement of a transistor, how non-linear is the transistor, everything they do. Once they do that, they know that, okay, now they can design an amplifier much more easily. Okay.
Yes.
So they know that for every micron of device, how much current I can burn, how much GM am I getting. So all those things, they have it in their thumbs. So they can easily start designing. So, please do not restrict yourself to this course only. So if you have any doubts and you have tried it out, you can email me and I can help you get these things sorted out.
Yes,
So this
definitely,
needs actually, honestly, this 2 hours is not enough to train in this. You need exactly 1 week. 1 week,
Yes,
every
definitely.
morning 3 hours of introduction, and afternoon do this, go to the lab and do these experiments. In 1 week, you will get a full flow, not only op-amp design, there is op-amp design, then comparator design, then switch cap amplifier design. All these things can be done systematically in 1 week. So that is how, reading the textbook won't help you. That is what my bottom line is.
Yes, we will be connecting you so that we can basic things that you were telling, that is the building blocks type of thing, that for designing any kind of things, what are the minimum things requirement, because for linear circuit we have to always do for op amp, and comparator is also a minimum block for any kind of regulation or difference voltage. So these we can design, and you can check that whether the every designs has been really everything we have explored or not, and
Right.
then we can make a like manual or kind of worksheet type of thing, so
Right.
that it can be like in future we can use it as a standard reference or standard experimentation. Okay.
Right. Yes. And
So you
another
can-
thing is that a lot of all the attendees are faculty. So if you have your own hands-on experience, then your students cannot fool you. For example, I give some work to my PhD student and tell them, okay, why don't you design this op-amp? They say they'll take 1 month. I said, let's sit together. Let's finish it in 2 hours. Okay. So,
Yeah.
so basically, if you know how much it takes, then you can manage your students properly. So
Yes, that is true. Actually, we are not getting anything in the, but we have hardware because we have started with several hardwares in our university. But what the students, they are not, I think they are telling about simulation, but we have SMU in our lab, Kitle, and we have LCR meter that you are telling for device characterization also, CVN and IV, and the simulator also, solar simulator. And for that we can do any kind of characterization and the hardware like, and if we simulate the analog circuit device that you were telling, so if we compare that, we can find several, we can extract several real parameters that anything can we can give in future, we can use it in real life applications. And this is, I think, good paper we can communicate also for that.
Yes,
But the
yes.
students are not so much motivated. They are always trying to like do only the simulation, because the simulation is clear to one if they know the theory and the background. Only the simulation is not be helpful,
Right,
because you
right.
have to know that what are the physics underlying it. If you are not able to do that, then simulation is not be enjoyable. No,
Right. True, true.
in that case, everything, even I think simulation is done, only the physics is required. But sometimes I see that several people, even in chemistry background, they are doing the hardware when I like anything than better than us, because they know that what is happening and why. I don't
Right,
know they don't know the principle, but they can do the experimentation.
right,
Okay,
right.
hardware experimentation. That I have seen. But without knowing the physical principles, simulation cannot be Excel, cannot be done in Excel way.
Right.
Is it?
Yes, yes,
I
that is true. So actually, my advisor Azavi, he used to
yes,
be hands-on. He would go to the lab and
yes,
do.
if there is a
So
scope for lab, always you do the hardware first. So
right,
and the simulation simultaneously.
right,
Then
right,
you will be learning that what is happening and what is happening and why it is happening.
right, right.
Otherwise, it is not will be clear.
So we'll take a 5-minute break, all those who
And
are there, and then we'll get into the
yes,
op-amp
yes.
design, and I'll start the layout also. I'll explain what is the dummy and why we need the dummy and all. I'll start from the biasing circuitry, and I'll start building the op-amp step by step. So um, is
Okay, thank you. Yes,
so in five
we are
minutes we'll
waiting for
join, right?
5 minutes. Yes. Okay, okay. Thank you.
Oh, thank you. Okay. So I'll start the class now. Hello. Hello. Hello.
Yes, welcome.
Welcome
Hello.
back all. Yes, ma'am.
Yes.
Okay, I'll start now. Okay, so now if you all of you if you have a pen and paper, so please write it down. So we'll start this thing of op-amp design with an NMOS input pair. We'll design the first stage first, and then we'll go on to design the second and third stage. Sorry, not so third stage, only the second stage. But if you know, if you remember, the NMOS has a tail current, input differential pair. So I'll start off with the now let us say the first stage of the amplifier is burning 1 milliamp of current. Okay, so please note down the tail current is burning 1 milliamp of current. Okay, so now let us start off with setting the biasing for that. So now keep in mind the bias transistor biasing circuit should draw 1/10 or 1/20th of the current flowing through the main device. So if 1 milliamp is flowing in the first one, in the op amp, first stage op amp, so that means let me burn 100 microamps in the biasing network. Okay. I'll use low VT devices because our supply voltage is less. So let us say our finger width is 2 microns.
Hello. One
Yes.
thing that before going to the design, what should be the our first assumption or first thing to be calculated, or first thing to be taken care of, that it is the participations or where to start with for
Okay.
a particular application.
Yesterday I had shown the slides. I said that okay, how to come up with the gain of the op amp. Point number one, right?
Yeah.
Then how to come up with the bandwidth of the op amp. Those
Yes.
two examples we have looked at. I will share those slides with you all, so you can probably share with all the participants. I'll email it to
Yes,
you.
yes, yes.
Okay. So that thing, and then the next aspect is the how do I find out the bias current flowing through the transistor? That will come from the slew rate. Okay. Now slew rate means how fast do you charge the capacitor at the output using as a current source. That defines the slew rate. So based on that, so these three, that means first of all the bandwidth is obtained, gain is obtained, then the DC current flowing through the transistor is obtained using these three information. And of course, then we have to iterate on it. We have to do multiple iterations to come up with the final solution, because design is never one shot. We have to first design it
One, although very silly questions. In that case, in case of biasing, how do you test that? What is the DC open circuit and short circuit in simulation?
which DC open circuit?
In any transistor or any, say you are trying to fix your quiescent point in the middle of the load line. So
Right.
I want to know the maximum saturation current as well as for the open circuit voltage, so that the transistor, one thing is transistor should not go beyond the power limitation. Again, that the cool point should be in the middle of the mm,
Load line.
load line. And the thing is that we are now we say we are want to measure the open circuit voltage and short circuit current for that stage. Okay.
Okay.
So
Okay.
in the DC. So in
Okay.
that.
So here I want to make a small point that load line concept and the quiescent current concept and all is used mostly in case of discrete component design.
Okay.
Okay. It is not actually used in an integrated circuit context because integrated circuit, what happens is that everything is happening inside the chip. So
Yes.
the load inside it is all internal. Now, the reason we don't go with that load and the quiescent this thing is because we go fully differential circuit, and we want to maximize the swing. Okay, so the output voltage is defined by the swing requirement. Okay, so and we usually set the output voltage of the device, open circuit voltage, close to the VGD by 2, supply voltage by 2.
That is the load line midway between that.
Midway, always.
Actually,
in IC,
always
we always
midway
do that.
between.
Yes.
Actually, we cannot find, because the load is connected, even if it is IC, integrated circuits, although the contacts, the pin configuration, that the pin outside the chip, that are coming for the load and the VCC. Okay? Now, so always we are providing these things. Now, if I measure that what should be the open circuit voltage, that is load is open, and what should be the our short circuit current, because directly what we are taking about that using inductor and capacitor intelligently, I think that way we can measure also. So
that also, yeah, you can measure, but usually most of the internal inside an IC, the load, there is no, most of the load is typically capacitive. So there is no DC current flowing through the load, except at the interface of the chip where you have to drive a speaker or something. When you have to, that time we use common source amplifiers, so that source follower amplifiers, so that we can drive with high currents and all. So inside the IC, it is mostly capacitive load. I would say 90% of it.
That is the parasitics. You are telling about parasitics, no?
No, not
load.
parasitics.
Oh, even in the load you are connecting in between.
Yes. Because the sampling network, you want a certain capacitor.
Yes.
You want to build a filter, you want to have a certain capacitor to do the filtering operation. So all these are, so 90% of them are capacitive load.
Okay. So then you directly cannot measure, I think. Directly cannot measure. You have to think in a particular way so that any AC load can be directly, it will be converted to some large signal or kind of thing. That way we can do. Maybe, I don't know. No, that is the thing. Open circuit voltage and short circuit current, I think with DC, we cannot measure in the integrated circuit simulation.
In simulation, we can measure. In simulation, using that
We can do.
Yes.
Okay. That is the way. That is also good.
Just using that capacitor the way I showed for the GM and RO measurement.
That I am telling. Yes.
That you can do. In simulation, you can.
Okay.
So now let us say we want to 1 milliamp is the tail current flowing through the tail transistor. Okay. And so 100 microamps is what I'm going to burn in the transistor. Okay. But I have no idea. I'm using this transistor for the first time. So I'll do some iteration. So and I want to maximize the swing. I want to have compliance voltage of 100 millivolts, VD-SAT of 100 millivolts. Okay. So this is what we are going to do. So I'll instantiate a transistor of 1 finger 2 micron device. Okay. So as I said, it should be 100 microamps of DC. So I'll pump in this DC current here. Okay. So first I'll build the current direct connected things. Okay. Now I'll instantiate a voltage source. Okay. So the voltage source is instantiated. Now I'll simulate. Okay. So you will see that we'll design a 60 dB op amp, and it should not take more than an hour to design it. Okay. I'll do DC simulations to find out how much is the current flowing. So let's run the simulation. and results, annotate DC node voltages, results, annotate results, DC. Okay. So now you can see that this one is drawing 100 microamps of current. So here I have to look at the VLSI. Okay, so I'll go this route. So I'm not able to find that option at this point. So now let us see what is the VDSAT of this. Where is the VDSAT? VDSAT is 200 millivolts. Okay. Now my question, so that this is where I need all your help so that I know that we are on track. Okay. Now my bias current in the biasing network is 100 microamps. Okay. My VDSAT is 210 millivolts, but I want the VDSAT to be 100 millivolts. So what can I do to make the VDSAT 100 millivolts? Attendees, please type on the chat or something. So what should I change here?
So we have to go into the deep saturation.
How do I reduce the VDSAT?
Yes, that means
Soumya?
that means you have to towards the mode saturation. So that means
I will just increase the W.
increase the W.
Yes.
Yes.
If I increase the W,
Yes.
let's see what happens.
Yes, yes. ID will be more. If the drain current will be more.
But then drain current, I'm keeping it constant.
Constant. Okay.
Because I didn't change this. I am changed. Still, it is 100 microamps.
Okay.
Right?
Okay.
I did not
So
change
actually,
that.
I just want to say that you are increasing the W for the PMOS transistor, right?
No, for the NMOS. This is an NMOS.
Okay, okay.
Okay. So you saw that VDSAT has come down 158 millivolts. That is not enough because I want 100 millivolts. So what will I do? I'll further increase it. Now notice how I am increasing it. I am not increasing the width by making the finger width more. I'm keeping the finger width the same. I am making it, keeping the finger width too. I am doubling the transistor. Okay. So now let's rerun the simulation. Okay. So now let's see results. Print. Now what is the VDSAT right now? 121 millivolts. Okay.
It is such an ID
will stay at 100. ID will stay at 100.
ID
Because I'm
saturation.
pumping. Yeah, because
ID
I'm pumping 100 microamps here. So this
Okay.
is staying at 100. You can see that it is 100.
Okay, it is 100.
Okay. So now I'll say that, okay, I'm okay with 120. Instead of 100, 120 is okay. I'm happy with that. Okay. So we'll stop at this point. But the problem is that I have used minimum channel length here. In low VT, the minimum channel length is 240. Now that is not good because my current source should have high impedance. So what will I do? I'll make it bigger channel length. So let's say 480. 0.500 nano. Okay. I double the channel length. Now to pump the same current and maintain the VDSAT, what should I do? I double the channel length. What should I do to maintain the same VDSAT and carry the same current? If I double the length, what should I do with the width? I should double it, right? I
Yes.
should double it. So I'll make it 8 fingers, each 2 microns, resulting in a 16 micron device. I've doubled it. Okay. Now let's do this. So we are just looking at the drain current equation and just manipulating based on that. We are not doing anything. Okay. It is very straightforward.
Oh, you are only the W and L that
Yeah,
you were changing.
Yes. Yes.
Size. size
Right.
you are changing.
Okay, so now let us see what is the VD sat. VD sat is 132 millivolts. It's okay because I have increased the length a lot. Okay, and my VD sat is 132 millivolts, so I'm okay with that. Okay, so that is the amount of current that I am flowing right now through this device. Okay, so I have it's a 16 micron device, 132 millivolts. This thing. Now you can notice that my threshold voltage has reduced because I increased the channel length to 500 nano. 16 micron device. Now, this ideal current source, I'll now replace that with a resistor. Okay. So, so 1.5, 100 microamps, so 1500 divided by 100, 1.5 kilo ohms is what I put here. Okay, so let's make sure that the ideal current source is we should put actually, oh, this became more, 835 microamps, so instead of 100, so it should be 10 kilo ohms. It should be 10 kilo ohms. Little more than I put 12, 126 microamps. I can reduce it further by making it 15 kilo ohms. Okay. So we are close to 100 microamps. So now everything is real component. There is nothing other than a real component, right? Resistor is real, and a transistor is there. Now it took us roughly, I would say, to take this iteration iteratively. We'll find it. Now I'll mirror this and build the current mirror. Now keep in mind my transistor has to burn 1 milliamp of current. So I will connect this, or let me label this as V bias N. Okay, so I've labeled this as V bias N, and I put this over here, put this over here. So I just copied that same transistor, but this transistor is carrying 1 milliamp. If I have to carry 10 milliamps of this, so what will I do? I'll put a 1 milliamp of this. I'll put a multiplier of 10. Now you see how I have used a multiplier and a finger. So now the current flowing through this will be 10 times the current flowing through this. Means the current flowing through this device will be 1 milliamp. Am I clear?
Actually, the current flowing through the resistor that is being directly fed to the gate terminal of the MOSFET, right?
Yes. Yes. Yeah, it is like this. Yeah. Yes.
Yes.
So all the attendees, please unmute your microphone. Let's make it interactive. Okay, just unmute your microphones and talk freely. Okay, that's the best way we can learn and have the session. Okay, so now I have made this 10 times bigger because I put a multiplier of 10. Okay, so I put a multiplier of 10, and because of that, I should be carrying 10 times more current here than here. So that means this will carry 1 milliamp. Now, the input differential pair will be what? I will copy this here, and I will mirror this F3. I will copy this sideways. Okay. So make sure that they look like differential. And for now, I'm assuming that I can somehow magically I have a deep angle process. Okay. So now, if this is carrying 100 milliamps, 1 milliamp of current, this in the DC operating condition will carry 500 microamps of current. Now let us find out what is the width and length of this transistor. This is a 500 nanometer length transistor. Width is 16 microns times 10, which is 160 microns, right? Now, I should then, this is carrying half the current of this. So then this should actually be both of them. So I'll change it together, all selected. Okay. I would make this 5 fingers, 5 multiplier, because they are carrying half the current at DC. Okay. So I have done that. So now you can see that both of them are 80 microns and 80 microns. Okay. Am I clear? Everybody is up to me with this?
Sir, can you please repeat the part again once again?
So here 100 microamp is flowing, right?
Okay.
And here I made this 10 times bigger
Okay.
by using multiplier. I multiplied the number of transistors. It became, so it is carrying 1 milliamp of current, right?
So
Now
it's getting 10 times larger.
10 times larger. Okay, so that's what I've done. 10 multiplier. I'm putting 10 of these in parallel. Now these two transistors are the input pair. So let's call this as V in P, V in N. Okay, these are the two input to the amplifier, V in P and V in N. Now this has to carry how much current? 500 micro and 500 micro. Am I correct?
Yes.
To carry 500 micro, what should be the size of this? It should be half of this, right? So I
Yes,
made it for
because it is
multiplier of
equally
5,
getting distributed.
right?
Yes.
Because under DC bias conditions, both will carry 50% of the tail current
Yes, because it is getting distributed equally.
equally. Now I'll make the multiplier 5, correct? Now I have exactly done that. Okay. Now after I have made this multiplier 5, now the problem is that my channel length is 500 nano. If my channel length is larger, will my speed be high or low? Low speed, right?
Low speed.
But the speed of the operational
Low
amplifier
speed.
depends on these two devices. The input device, right? The GM of that device. So I have to, in order to maximize the speed, what do I have to do? I have to change the channel length. So I'll go back to 240.
Trying to decrease the channel length.
I reduce the channel length.
Yes.
If I reduce the channel length, what should I do with the width of the transistor? Exactly make it half again, because I reduced the channel length by 2. So I should reduce the width by 2 also,
Yes.
so that the W by L stays the same, correct?
Yes, the aspect ratio will be same.
Yes. So then that means I should change that by a factor of 2. So I'll make it 4 fingers here. Am I clear? So did you understand the progression
Hello,
from?
always we are going changing the length of the channel or whatever be the width of the device. Then we are always trying to do the W by L ratio to be always 1.
No. I never said it is 1. I'm trying to maintain a W by L ratio so that the current appropriately
Yes, it
splits.
actually Sai is trying to maintain the correct ratio.
Correct ratio to make the current flow properly.
Okay,
Right.
current flow
So
properly, not that always W by L to be.
No. So here I have maintained a certain W by L. Okay, 100 micro. I made this 10 times bigger. Okay, so I got 1 milliamp of current here. Now this current is splitting equally. So I copied this transistor over here, but it is carrying half the current. So I made the width half. How do I make the width half? By reducing the multiplier by a factor of 2. It reduced by a factor of 2, 5. Now I want to reduce the channel length because I want faster transistor. So if I have to reduce the channel length, then I better appropriately reduce the width. Otherwise, my VDSAT will further reduce. Okay. So please remember the equation of the current, equation of the transistor. If that is visualized, you now play with that. That's all you need to do, nothing more. Okay.
Yes.
So now you make this width. So now this current. Now
Equation of the current means the drain current, right?
Sorry, drain current. Yes.
Yes, sir. Okay. Yeah.
Now I have to set the DC common mode, input common mode. What should be the input common mode? What is the saturation voltage here? 130 millivolts. We saw, right? VDSAT, correct?
Yes.
And this is VDSAT was 130 millivolts. 130 millivolts. So I cannot operate exactly at VDSAT because it is risky. So I'll put 50 millivolt margin. So I will make sure that this voltage never goes below 180 millivolts. if this voltage never goes below 180 millivolts, then what should be the DC voltage here for the same for the current to flow? 180 millivolts plus whatever is the gate source voltage required. Okay. So 180, because the channel length is smaller, the threshold voltage is larger. So this would need roughly 400 millivolts. 400 plus 180. So I will set this common mode at 600 millivolts. Okay. So that means I will define the input like this. This defines the common mode 600 millivolts. Okay. So this defines 600 millivolts. Then I define the input over here, and this is defined as DC is 0, AC is +1, input P, and this is DC is -0, AC is -1 because it is differential. One goes up, other goes down. So that's how we define differential signal. So now this is there. So I always maintain symmetry. So without that, I don't like to see if things are asymmetric. So this length and this length I purposely kept it same. So please maintain this because this helps a lot in terms of when you're doing the layout and all also, that shows that things are meticulously done. So I have applied the common mode at 600. Okay. So now let us see that is there. Now I will put the PMOS. Okay. Now let us find out the reason how we are going to put the PMOS. Now, Somo, this is the transistor NMOS. Okay. This is the NMOS that carries 500 microamps of current, correct?
Yes, sir.
Now, if I have to carry the same amount of current via PMOS, what should be the size? Where should I change here? What should be the size of the PMOS to carry the same amount of current? PMOS mobility is how much? Half of NMOS. So PMOS
I think the length should
Does it-
decrease.
No, how length is minimum already. We are minimum length, right?
So
We have to make the width larger, right? Because its width has to be twice as large as the NMOS, right? So that means I'm going to instantiate a PMOS now.
Actually, in PMOS, whatever the width is, but in case of NMOS, it becomes 2 times, right?
PMOS, yes, PMOS will be twice as big,
Yes, perfect.
right? So now you help me note down this size here. Total weight is 8 microns. Finger weight is 2 microns. Length is 240. Finger 4, multiplier 5. Okay, you have noted this down?
Yes.
Okay. Now tell me what should I do here. You tell me what should be the value. I'll keep the multiplier at 5. Okay. Finger width should be, I'll keep it at 2 microns. Number of fingers, I'll make it 8, right?
Yes, it will become 2 times. 4 into
16, right? 16 microns, right? Correct?
Yes.
And I'm keeping the channel length the same. Now, this is a current source load, right?
Yes.
Should we keep the current source load, the channel length at minimum, or should I increase it?
current source low? Yes, repeat it.
This is acting as a load, right? These two are loads.
Yes.
In the load transistor, what should be the channel length of a load device? Larger, right?
Yes, for the
To give more output impedance. So now,
yes.
Soma, please help me. I'm making this channel length 500 nano. What should I do with the width now? to carry the same current?
I think the width will decrease.
Width will?
It will decrease.
I made the length longer. So what should happen to the width
So
if I have to carry?
it will be larger.
It has to by how much?
2 times.
2 times exactly. So I will make this 16 and maintain this. Okay, I'm making maintaining the finger width of 2 because I want to minimize the gate resistance. Okay, so now we are almost done, but I have to set the bias voltage here. To set that bias voltage now, I'm going to copy this. Okay, I'm going to copy this, and then I'm going to copy this also. But this should be 1/10 of this, right? Now I am in a problem because this has to carry 1/10 the 1/5. So it is not a problem because I will make it 1.
Okay.
Correct? So okay. So and I will connect this like this. This is the V bias P. So if I connect the V bias P here, is that enough or do I need something more? What did we studied last time? We need a common mode feedback circuit, right? Okay.
So
Yes, go ahead.
they will be.
So I have to have a common mode feedback. Somebody has a question. Okay, so if nobody has a question, so I need a common mode feedback circuit. So I cannot connect this here directly because it won't work. Okay. So what I'll do is, what does the common mode feedback circuit? I'll now build an ideal common mode feedback first. Okay. So how do I build an ideal common mode feedback circuit? I take an I'll take an analog adder. Okay, and I have to average the two outputs. Okay, so the analog adder takes in VO and P. This we call it as VOCM. V output common mode. Okay, so I take this, then I give it to an amplifier. I'll use an ideal amplifier. Ideal amplifier is a analog layer. Voltage controlled voltage source. And I set the gain of probably 20. Okay, so I'll use this voltage controlled voltage source. Okay, and this is going to, what is the desired output common mode? VDD by 2. I will set this output voltage to be close to VDD by 2. So I'll have another voltage source which I can apply from outside. Let's call that as 0.9. And I call that as the desired output common mode. VOCMD. That is the desired output common mode. And I apply that to and this is should go and control the gate of this transistor. VCMC. Let's call this VCMC. Now I've connected this here. Okay. Okay. So now this is there. Now I will fire a DC simulation. Okay. Let us see how that where things are. Okay. So DC simulation is done. Now you can see that this is exactly carrying 1 milliamp. These are carrying almost 500 microamps, roughly. Okay, 500 microamps.
Yes.
And the common mode control voltage has come to 1.402. Okay, and you will see that this will be very close to this value. But it is not, because output common mode we had set it at how much? 900, but it is coming to 970. So the only way to improve that is by making this, increasing the gain here. If I increase the gain here, then this gets, did it simulate? So you saw that it comes down to 935. The output common mode is set to 935 millivolts. Okay. Now, so actually here I would then roughly need a gain of 80. Okay. So this is my 917. I'm okay with that. If it is 900, I wanted it to be at 900. It is at 917. I'm okay with that. I can adjust the this value.
Okay, so what will be the ideal value for this case?
Ideal value, we want it to be 900 because this is what we have desired. We want it to be 900. Okay. Now the gain of this amplifier, right now the common mode feedback circuit is ideal. This is called the ideal common mode feedback. So this is doing the common mode sensing, and this is giving you the feedback and amplification. Okay. So now let us find out what is the gain of the circuit. Okay. So I have to run an AC simulation. So I'll run an AC simulation here.
Yes.
And I'll go from 10 hertz to 1 gigahertz. One gigahertz, and as I said, logarithmic 40 points per decade.
So if you take the sweep time as linear, will it not be much efficient?
No, it will be much worse because
Okay.
it will find too many points. And logarithmic scale, because we plot x-axis in logarithmic, right? So why plot simulate linear? Because always we plot x-axis in logarithm, right? The bullet
Yes,
plot.
sir. Yeah. Okay.
So we should do exactly what we are seeing. So now, if I do this, now I have to find out the gain. I go to calculator, I do VF, so VOP, then go in there, VON, minus, then V in P, V in N, minus, you divide, then dB20, output setup. This is called AC gain. Okay. Now, when this gain crosses 0 dB, so I'll say cross threshold value 0, edge 1, falling, means the gain is reducing, falling, single, okay, outputs, setup, get expression UGBW, unity gain bandwidth. So I've added both of them. Now I will simulate it. This will tell me the. So the overall gain that I'm getting from this circuit is close to, this is a huge bandwidth because the gain is low. Now let's go to 10 gig. Okay, so it tells you the bandwidth is 6 gigahertz. Okay, I have no load, so obviously it is going. And the gain of this amplifier is 28 dB. roughly 27.5 dB. So that's the maximum gain that I can get at this point using this device. Okay, because I have made this length, channel length longer. Okay, and my common mode feedback is working. This is what I'm getting. Now I have to enhance the gain. So what will I do? If I have to increase the gain, cascode, right? Okay, so now let's go and cascode. I'll move this up. I'll now copy this transistor, copy it over here, copy this over here. Now remember, I told you yesterday that we have to set the bias. This cascode bias is set by another device in the middle. So I will put this device. See, in schematic also I pay close attention to the symmetry. And I also want you all to pay that close attention. The circuit should look perfectly symmetrical. Okay, so what I'll do is now I'll use this one to set my current. And this should be very, very small device. So I will make this 1 micron. Okay, so and this one I will connect this to this, and I call it P cascode bias. So first, before I run the AC simulation, I want to make sure that the thing biases are connected. Everything is in saturation. So now let's see if this is in saturation or not. This is in saturation because this VGS is this is VGD is less than threshold voltage, so this is in saturation. This is also in saturation. So my overall thing is 600, 800. Yeah, so this is pretty well, very well in saturation. Now let's see how much current this is carrying, 149 microamps. So I would now carry more current here. I will reduce this current by making this number of fingers 8 and 2. Okay. So I have reduced the current flowing through this. This is pretty much close to that. This gets into triode. Now, in order to now I have to increase. This is now getting close to linear region. This transistor. Okay. What should I do with the size of this so that this voltage goes up and this comes out of being linear and gets into saturation? Anybody? Soumya? I have to boost up this voltage. So how will I boost it up? By reducing the transistor width.
So I'm keeping the length same and reducing the width.
Then the VGS of this device will increase
Okay.
for the same current, because the current is decided by this.
Yes.
So same current, if I'm reducing the width, then obviously the VGS has to increase to accommodate the same current, and therefore this voltage is going to increase. And now this comes back into saturation. Okay, I will make it a little better by making this channel length 400. So now I increase the channel length, so the gate voltage is further going to increase a little more, and thereby this really comes back into saturation. Okay, so this is how you play around. You just play with the width and length. You have to know the transistor equation and just play with that. Now let us find what is the gain. What is the gain now? Gain increased. Okay, what is the unity gain bandwidth? Bandwidth dropped to 4.95 gigahertz from 6 gigahertz. Because the gain increase, the bandwidth is certainly going to drop. So this is probably the maximum you can get. You can no, sorry, I'm wrong. I can further increase the gain. Now here I have used minimum channel length, right? So now what I'll do is I'll increase the channel length 500, because this is a cascode device. If I increase the channel length, I doubled it. So I need to carry more current, carry the same current, increase the length. So I have to increase the width. So I'll use multiplier here. Sometimes I'm using multiplier and fingers just to illustrate it. Okay, let's see what happens to the gain. Gain went up further, 42 dB. Okay, so this is the overall gain. This is the maximum you can get right now. If I have to further improve the gain, I have to cascode on the load side also. Okay, but if I now connect a second stage which gives me 20 dB of gain, which is the gain of 10, I can easily cross 60 dB. Okay, so now another thing that I can do is, of course, I can change from this one, from low VT device, I can change it to regular VT, and that will also enhance the gain. Okay, so that is also going to enhance the gain. So you can see that the gain went up to 43 dB. Okay.
Okay.
And the
So
unity
what is
gain
my
bandwidth
bandwidth
has
then?
come down.
Okay. Yes, it has come down.
So now, see, I just had the equation of the current transistor equation, which square law equation. You don't need to know saturation. Transistor might be in velocity, saturation, short channel effect. Everything is there. It doesn't really matter. But transistor follows where the only thing it changes the exponent of the device. All you have to do is, if width increases, what happens to current? What happens to VDSAT? If length increases, what happens to current? What happens to VDSAT? Now that concept stays the same whether it is long channel or short channel. That doesn't change. Only thing is that the relative magnitude with which these things will change is a function of whether it is long channel or short channel. That is all. Okay. So it means if you understand that equation, so all you have to do is, and you have your first stage design. So I started off from these two devices. Okay. Then I built this device. Then I built these two. Okay. Then I built these two. So then I built these two. Then I have to increase again, bring in the cascode. If I have to further bring in the again, I can bring another cascode here.
Yes. So that will be connected to the lower side.
Which one? The other cascode will be on the PMOS side. This is the NMOS
yes.
side, right?
Yes.
And
The
the
upper
other cascode will be connected over here on the top side.
Yes, the top one, the upper one. Yeah.
So so now how does the op-amp design begin? I begin with the foundation, which is this. Okay. That means I dig the foundation first. I set the bias current. Then I set the foundation concrete by this tail current. Then I start building the pillars by these are the 4 pillars of the amplifier, these 4 transistors. And then I build the walls by cascading it, enhance the gains. It's a very simple process. You start off systematically, you know what is the current and all, and you start building it up. Okay, and it is not that complicated. It is very simple. And once you build your first amplifier, you are done. You can just modify that amplifier and build it. So you saw that within 1 hour you have the first stage done. Another 5 minutes we can get the second stage done. Okay. So this is any questions on how I proceeded? I think Arijit, any doubts? Your microphone is on. Any questions on this?
I think now it is there after you can start the next as there is no query till now.
Okay. So now I'll join the build the second stage.
Yes, please participant, please mute your mic. What is happening?
Hello. So okay. So now I'll build the second stage. Now keep in mind for the proper compensation and the proper stability, let's use a rule of thumb. I think Arijit's microphone is feeding back. Okay, so now we will build a second stage. Now, as I was saying, the rule of thumb, because we'll get into the stability, two-stage amplifier, so we have to make sure that the two-stage is stable. So how do we do that? If the current flowing in the first stage is X amperes, the second stage, if it is between 3 to 5 amperes, then we can compensate it very reliably. I won't go into the math and all those things because that can be mathematically proven. But let us assume, take that as a rule of thumb. So I'm burning 1 milliamp or 500 microamps in each branch. So in the second stage, in each branch, I'll burn 5 times more, which is 2.5 milliamps.
Please, students, please attend. Please switch off your phones. Please.
I think Arijit is not present.
Orijit, hello. Who is Orijit?
Arijit Day. Can you please mute your microphone? Okay. So based on the rule of thumb, now the second stage, because the first stage is NMOS, the second stage has to be PMOS. So I will copy this. So I'll apply the input. Now this has to be minimum channel length because this is the input device. So means it is 240. Okay. Now this has to carry 5 times the current that is flowing to. So I may reduce this. So this should become 8 microns. I reduce the channel length, so that becomes this thing. This should carry 5 times more current than the first stage. So what I'll do is I will make it 5 times more. So I'll make it 40 here. Finger 40. Okay. So both of them are now bigger devices. Okay, and now that is there. Now the load has to be connected. Load will be NMOS load. So I will connect this. And also another thing is that these I will make it LVT so that I get the bandwidth. Low VT devices will get the bandwidth that way. Yeah, both of them are low VT. Then I'll plug in the NMOS devices. Now NMOS devices, they are acting as load, so I can make the channel lengths bigger. So, and they have to carry 5 times more current. So 5 times means I'll make it 20 microns, 20 times here. So it should be 2U. But I'm going to make this 500 nano. I double the channel length, right? So I'll multiply if I increase it here by a factor. Okay. Put in the ground. The same bias voltage can go in here. And this is UN, UP. Okay. So now let's see that, make sure that the biasing has come up correctly. So let's see the bias here. Oh, I have to set the common mode feedback. Sorry, I did not set the common mode feedback properly. So here, what I would do is I would put a resistive feedback. And I will sync some current here. And check that it has biased upward. So this is drawing 263 microns. This is 260, 135. So I'm just making sure that this is pretty close to uh, here. I will draw a little more current so that, or I will increase this. So I'm just making sure that the bias point is correctly set. So now it is 5 milliamps. So 530 here, and I should bring this to 100. So there's some problem with this. So right now the output voltage is defined by, so there is 800 millivolts here, so I should bring this down to 300. So 400 roughly. I'm just trying, I have to make sure that the swing is also optimal and this output common mode is set at 900. So 391, so 300. The connector is correct, so I have to draw the so okay, I'll put the same ideal common mode feedback around this so that we can set the output bias correctly. So here what I do is I'll take this, okay, desired is at 0.9. Now I understand why it is, because here we had set it to 0.9. This should have been set to a very high value, 1.2. Okay, so now it's going to. So here I would set the desired to 1.2 volts. And here this one. Okay. So now okay. So this will come to So now this is roughly 1 volt. So now let me tell you what was the mistake when I cascaded. When I wanted to build a two-stage amplifier, then the output common mode here should not be set at VDD by 2. If I set this at VDD by 2, then what happens is the VGS of this becomes very large. Okay. Then the VD sat of this will be large and the swing here will be compromised. So here I would say I have set the VGS of this very small 600, so that the VD sat here will be probably most likely 200 millivolts here. So results, we can print DC operating point. VD sat here would be roughly, how much is it? 324. We can further reduce it if I set this common mode to 1.3. Okay. So if I set this desired common mode to 1.3, then it will come to 200 millivolts. Then you get more swing. Okay. So so if I set the output common mode of the first stage should be such that the VD sat of the next device is very close to is 100 or 200 millivolts. Okay. And then I set size this, and I'm drawing roughly 5 times more current, 10 times here in this case, more current than this. So it will roughly it will be almost stable at that point. And I'm sinking some current through this and giving a common mode feedback here. Now let us find out the gain of this. Okay. So we have out P minus then V P V output setup. I will say that overall gain stage gain. Okay. Now unity gain bandwidth has to be modified because now I'm looking at the this one, the out P out N. So first stage gain and then the two stage gain. Okay. So now you can see that two-stage amplifier has a bandwidth of 2.5 gigahertz. Of course, it is not compensated. Phase margin would be worse. Two-stage gain is given by this yellow line. Two-stage gain. So that means there is something wrong in the second stage. What is wrong in the second stage? Oh, it should be dB20. Was this also dB10? Oh, no, it was dB20. So that's why I have that wrong. It was showing that the second stage is giving less gain. Okay. Now you can see that the two-stage gain gives us a 62 dB gain. Okay. So the overall gain of the two-stage amplifier is 62 dB, and that was our target. And the bandwidth of that is 2.6 gigahertz. Of course, it's not compensated, so that will become. We have to make sure that it is compensated and gives us the right phase margin. Now, just want to reiterate this fact. So when I was initially trying to bias it up and look up the bias conditions, it was wrong because I had kept the output common mode of the first stage as VDD by 2. When I build a two-stage amplifier, the output, the first stage common mode should not be VDD by 2. It should be such that whatever transistor it drives that with minimum VD sat. Am I clear? So, and in order to reduce the VDSAT, VDSAT can only be reduced if I reduce the VGS, because VDSAT equal to VGS minus VT. So I reduce the VGS of this PMOS by increasing the output common mode of the first stage. If I increase the output common mode, then the VGS reduce, VDSAT of this is going to reduce, and therefore I was able to bias it. The bandwidth of the phase margin of this will be a little poor, because I'm burning 10 times more current in each branch. So if I have to reduce it, I would have to reduce this by, I would say, I would have to burn a little less current, so that it gives us the right value. Okay. So phase, I can stabilize it in a much robust way. Okay, so with this, any questions on this so far? So now the currents are much better. So this is going to give us good phase margin. Of course, I have to still do a compensation. Okay. So the overall gain of this thing is 60.4 dB, 60.5 dB, and we can still make it 70 dB if we do a little more tweaking. That can be done. So now, any questions on this? How I went from a single stage to a second stage? Any questions, Soumya?
No, sir.
Okay. Did you notice the mistake that I made, so that nobody else makes a mistake? I was doing it.
Yes, actually, it should not be VDD by 2. That
Yes, it should be such that the second stage, this output is driving the second stage. The VDSAT of this should be small. Therefore, this here it should go up. If this were a first stage had PMOS input, then the output common mode should be brought down, because it is going to drive an NMOS in the second stage. Is that clear?
yes, sir.
And yesterday also I showed that this is going to give you this kind of there will be a VDS here, because there will be some current flowing through this, resulting in this VDS, and this gives you more swing at the output. Okay. So is that clear for everybody? So we started from this, then we added this, then we went on to add these two transistors, then we added this transistor, found out the gain, then finally added the cascode transistor, along with it the biasing, and then we went on to build the second stage amplifier. Am I clear?
Yes, sir.
If no further questions, I think we can, is that okay? It's almost 4:20, so tomorrow I'll go into full custom design for using standard cells and all.
Yes.
Sir, can I ask one more question?
Yes, go ahead.
Yes.
Sir, is it possible to design the layout? I mean, from the schematic?
Do the layout yourself. Okay. So then I'll quickly show the layout of this. Okay. I'll start the layout at least today. So layout should be done, of course, in a half circuit manner.
Yes.
Okay.
Okay.
Now, layout, I think in NTPL, they have in the first session, they have shown from schematic to layout. They have shown us that how to start with the layout and how to
Yeah, so I think
parameters.
they are going to use the layout Excel flow. So I do not use the layout Excel flow. I
Yes,
still
yes,
use the
they
old
had
fashioned.
Excel flow.
They are
Okay.
using the Excel flow. So basically what I would do is first I'll do this. So this transistor is this one. So I'll instantiate that over here. What was the size of Excel actually takes it directly from here. So this is
The screen is not visible.
Oh, screen is not visible. Okay. Where is the Why can't I
Excel,
show
how,
this?
what is the problem and issues? What are the issues?
No,
in
Excel is better. Excel is better.
Better,
Excel,
okay.
Excel is better. But
Actually, ma'am, we have been
I'm old
but
fashioned. I
actually
think
Old
I
yes,
cannot
fashioned.
share. I cannot share the screen. Something went wrong.
Okay, okay, maybe.
I don't know why sharing the screen window is not coming.
Okay.
So what happened? Ah, now I think I will share. So, so here, so this is I'll make 2 micron, 10 fingers. So make sure that I choose layout Excel is much better. So I still teach. So 5, 4. Okay. So this would be 4 fingers. Okay. 2 microns each. Okay. And I have to add 2 dummies. So I'll make this 6 fingers. Okay. So I will add 6 fingers. So out of these 6 fingers, this top and bottom are dummies and rest all are the actual transistors. And I have to have 5 multiples of this. So I will put them 5 of them.
Hello, পেয়েছো? কি প্রেম, হ্যালো হ্যালো হ্যালো, ইয়েস, আমি এক মিনিট ধরো আমি একটু হোস্টকেই জিজ্ঞেস করে নিচ্ছি।
Hello, madam.
হ্যালো প্রেম, Professor Bhattacharya is not able to enter. He has not got any link.
Yes, ma'am. We have sent the message also, and Savik saying into it.
Now, yes, you
We
sent
have
once again.
mailed to Bhattacharya sir,
No,
but
you
kindly look
directly,
into Savik
you
sir. So I have
directly.
forwarded everything to Savik sir.
No. Today you just cannot directly give a link immediately. Hello.
Yes.
Ma'am, ask him to log.
Yes, you directly give a link. Otherwise, Shovik's link is not.
Ma'am, one more meeting is going on.
Maybe
Savik
some
sir,
problems.
kindly
Yes,
look into the
yes.
matter, sir. Savik sir,
Please. Yes.
Yes, ma'am.
Savik, kindly look
It
into
is
the matter, sir.
already sent by him just now.
But till now he is not getting.
I also give you the link. Please, if you can send it, because
Okay. I am requesting Prem to send another link, because in the earlier days also I felt same problem. Okay, so if you Prem, you can generate one link and send to him, and I'm seeing again. Okay, and excuse
Okay.
me, Professor Shah, that I am
Yes.
disturbing you. Actually,
I think I'll
it's
stop
not
at this point. I can continue tomorrow with the layout if that is well.
Yes, that can be, but you can continue with the 5-10 minutes, because he's not able to join. That's why I am disturbing
So no
him.
problem, no problem. Yeah.
Okay.
So I was just showing that you put in the this thing.
Yes.
So you put in these 5 transistors on one
Yes.
half, okay, and then the other half you should put those transistors facing each other. Okay. So
Okay.
that way.
So you
the
can
different-
continue up to 5 to 10 minutes. No problem. I'm just.
I think it will be too quick in 5-10 minutes. So I think I'll wrap
Okay.
it up at this point. If there are
Okay,
no
okay.
further questions, we can continue tomorrow from here. So I just wanted to
Okay.
make sure they understand from one transistor how we started building up everything.
Yes.
gradually.
Yes. Hello.
Okay.
Hello.
If no further questions, I'll stop the call. Thank you all. Okay, so I'll wind up then. Soma, everything okay?
yes, sir. Okay, sir. I understood today. Okay, sir. Thank you, sir.
Okay, thank you all. Thank you for attending. We'll see you tomorrow.
Shovik,
Hello, Shobik and Prem. We are requesting you to send the link which is directly to KGP dot not to send in rnet.in. It is the kgp.ac.in. I think you just check. খড়গপুর আইডি যেটা ac.in আছে সেখানে পাঠাও। হ্যালো মিহির, হ্যালো, ইউ চেক দ্য মেল। খড়গপুর আইটি যে তরুণদার মেলটা দেখো, অফিসিয়াল ওয়েবসাইটও নিশ্চয়ই আছে, ওখান থেকে কপি করে পুট করো।
আচ্ছা, স্যারের মেল আমার কাছে আছে, আমি চেক করে দেখি।
হ্যাঁ, তো ওখান থেকে তুমি ওটা প্রেমকে দাও, ওটা ভুল মেলে চলে যাচ্ছে, ওই জন্যই উনি কিছু পাননি।
হ্যাঁ ম্যাডাম,
হ্যাঁ
প্লিজ সেন্ড মি দ্য নিউ মেল আইডি।
হ্যাঁ, ও দিচ্ছে, মেয়ে দিচ্ছে। আচ্ছা, তুমি কি arnet.in এ পাঠিয়েছিলে? কেজিপি arnet.in এ পাঠিয়েছিলে?
না 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 না,
তুমি কিসে পাঠিয়েছো? অ্যাড্রেসটা
torun.k.bhattacharya@gmail.com।
না, জিমেলে জিমেলে পাঠিয়েছো, ওটা পুরনো মেল হয়তো।
torun.k.bhattacharya@gmail.com
জিমেলটা হবে না, তুমি ওই একাডেমিক মেলটাই দেখো, একাডেমিক মেলটা দেখো, ওর যে ইয়ের কাছে আছে।
Ma'am, we have forwarded the link in the WhatsApp. Kindly forward it to sir, ma'am.
হ্যাঁ দাও, আমাকে দিয়েছো?
Yes, ma'am. Look into.
You have get already. I already share you the link.
তুমি মেলে দাও, আমি নালে আমি এটা ইয়ে করতে পারছি না, তরুণ আছে ফোনে। হ্যাঁ, তুমি মেলে দাও আমাকে, আমি মেলে ফরওয়ার্ড করে দিচ্ছি। তুমি মেলে ওই মেলটাতেই দাও না, এটা তো এই সবচেয়ে সুবিধে। মিহিরকে দিয়ে করে, মিহির ফরওয়ার্ড করো ওদের।
হ্যাঁ, করছি।
আচ্ছা এইটা তুমি তরুণদাকে দিতে চাইছো তাই তো?
iitkgp.ac.in হ্যাঁ 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 হ্যাঁ
হ্যাঁ ওটা দাও।
ekb@ec.in
হ্যাঁ 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 হ্যাঁ
হ্যাঁ
পেয়েছেন কিনা? হ্যালো হ্যালো,
হ্যাঁ
হ্যাঁ পেয়েছেন? হ্যাঁ
হ্যাঁ
ইউনিটেক, হ্যাঁ পেয়েছি ঠিক আছে।
small shop.
শেয়ার স্ক্রিন, হ্যাঁ হ্যালো, হ্যাঁ পেয়েছি, কানেক্ট করেছি, ঠিক আছে।
আচ্ছা আচ্ছা ঠিক আছে
আচ্ছা দেখা যাচ্ছে কি? হ্যালো,
ও তরুণদা has joined?
হ্যাঁ হ্যাঁ আমি লিঙ্কটা পেয়েছি, এবার ঠিকঠাক আছে তো?
হ্যাঁ স্যার, হ্যাঁ স্যার।
হ্যাঁ yes
স্যার
yes
ভালো
yes.
আছেন
ঠিক-
স্যার?
ঠিক আছে।
মিহির বলছি।
ঠিক আছে হ্যাঁ।
হুম, হুম। Yes, Tarunda, welcome to our university. And once in the year 2013, probably, you have once joined and you have delivered one lecture about MEMS in our department.
Yeah.
And really, it was very nice that students were get motivated to learn about and to do some research work in MEMS. And I think today's lecture will also be very motivated and inspiring, so that students can learn out of your lecture. Thank you once again, and please, you can start now. Yes.
Thank you, Professor Shorkar, for inviting me, and also the other colleagues of MAKAUT. And I'm just sharing my slide, just 1 minute. Then can you see my slide?
Yes sir,
Yes.
it is visible.
Yeah, just 1 second. Slides. Yeah, so I think that all of you can see my slides, right?
Yes sir, yes sir.
yes sir
So I am Professor T.K. Bhattacharya from Electronics and Electrical Communication Engineering Department, as well as Advanced Technology Development Center, IIT Kharagpur. The last 8 years I have been working in two main activities of IIT Kharagpur. One is the Advanced VLSI Laboratory, which is the biggest VLSI design center in any academic institutes, including IITs. And I will also talk about this lab a bit. And also, I am heading the National MEMS Design Center, and which is a part and parcel of the design and fabrication activities of MEMS device, electronics and MEMS lab, E&EC department, IIT Kharagpur. And this Advanced Technology Development Center is, we are the founder member of this Technology Development Center, which hosts the interdisciplinary research, which incorporates any biological science or electronics, physics, or even chemical engineering can work together, and they can enroll. Suppose one student in the biotechnology department wants to enroll in electronics, then through this advanced technology development, which is an umbrella for providing the opportunity for interdisciplinary research. So that is Advanced VLSI Lab. With these short introductions, let me share you actually initially I thought of giving more stress, but when I see the motivation or this main scope of this workshop, then I find it is the VLSI domain. And then I will actually add VLSI as the main focus, and also would like to mention some of the interesting ideas of MEMS and how it can be interfaced with the electronics. The concept of co-design has to be brought into this field, because I will say that when you actually design any sensor, MEMS-based sensors or actuators, and also you are trying to design the electronic circuits for it, those two things cannot have two verticals, isolated verticals, but they should work together. You can call it a co-design. So they should comply. The device would have their lacunas and limitations, whereas the circuit would have their lacunas and limitations. But if you develop this together, then you will find the complete and holistic solutions for our society. So with this approach, let me just give you a start with the VLSI. Since the scope, you wanted to know about the scope of VLSI, so that is my responsibility to tell you about the VLSI, where we stand now, and being in the government as a national coordinator for MEMS design, the VLSI SMDP program, I have the responsibility to educate you, to let you know what is the present situations and what is the future for the next phase and all. So VLSI design and the current trends. So what is the current trends today? So let me explain. Before that, you should know about the how a VLSI design activities has been started. What is VLSI and what was 20 years, 30 years before, and what is now. And we are at the era of more than more. And so beyond more, what is happening and how it is going to be taken up by the academia, industry, and users. So the overview is that understanding the fabless manufacturing model. So as you know that India, we don't have really any good fab. Good fab means I'm comparing either TSMC or IBM or Global Foundry, all those international foundries, where you can go up to 5 nanometer node. But and also there are a few captive foundry from Intel. IBM actually sold to Global Foundry, and then TI, they have foundry and now, but we don't have any such kind of foundry, but we have up to 180 nanometer fab in SCL Chandigarh, and there is another small foundry in Bangalore that is called the Sitar, that is mainly for the defense activities. And also we have another gallium arsenides and gallium nitride group 3-5 foundry. It is in Gatek, Hyderabad. The scenario today in India. So in this scenario, probably if you want to take the same kind of boom as we have in IT industry, why not the VLSI design should have the similar kind of upliftment? And we thought of in our discussions that whether India can take the leverage of having a large pool of manpower in VLSI design. Because now the concepts of fabless manufacturing is coming up in a big way. And most of the industry, including TI, Qualcomm, all these big houses, you know, they don't have their fab at this moment. So they are working with with a chartered foundry, for example, TSMC or Global Foundry. And they actually design, and then they send the GDS2 file to the foundry, and they actually fabricate the chip on behalf of them. So that is the fabless concepts. So in this concept, actually, India can actually explore, because India, like an IT, they are already the world leader. But also in the VLSI design, we can say that in India, we have all the R&D and the semiconductor and VLSI industries, you name it, like Intel, IBM, Global Foundry, all are here, Micron. So all are here. So there is a huge requirement of manpower in the VLSI design. Therefore, I actually was inducted as the coordinator of fabless manufacturing in India, and to have a collaborations with a leading country like Taiwan, who actually the country of TSMC, the largest manufacturer of ASIC and VLSI world. I think 90% chips are coming from that fab. And as you know, even yesterday, they have made a breakthrough that they can go up to 2 nanometers. So they are now putting in the production trial the 5 nanometer. And but they are thinking of by 2023-24, they will go to 2 nanometer. Think of it, the concepts, where we are working in 180 nanometer in India. But none of the working in below, say 14 nanometer or 10 nanometer like that. Memory devices, especially if you look at the main is roughly 14 nanometer, Intel 10 and 7 nanometer like that. When I talk about nanometer, that means the source to the minimum feature. So, so I lead a team from government, from India, various institutes, and to TSMC, to the National Nano Device Lab in Taiwan, and we had a very strong interactions with them, and to take the collaborations like leverage from both the side. They are the fabrication hub for the chip, and we Indians can make the design. So why not we take the leverage of both and taking the synergy and develop more successful in both the countries. That was the main idea. And 2018, a delegation led by me was in Taiwan for 5 days. So that is the situation now. So why say your scope and all this? You have to know a little bit of what is the semiconductor manufacturing business model at this moment. If you don't understand that, then probably you cannot find where you want to place you and yourself. So long back, actually the companies like IBM and Intel, Texas, they have their own foundry. And they are taking care of the marketing, sales, the design of IP systems and manufacturing. So that is called integrated device manufacturing model, IDM models. That is in actually in 1970s, that kind of, when we know the name of IBM computers, then they do actually all the things. The design, they develop their IP, they manufacture it, and they also market it. After that, they thought of the concepts called fab-lite model. So what is that? The marketing and design IP and manufacturing. And they also put some partner foundry. And those companies are Infineon, Motorola, and ADI. So analog device. So they are basically trying to outsource their chip manufacturing from the foundry. So that is the fab-lite model. So if you look at from the integrated device manufacturing model, it is evolved to fab-lite model. Say in the early 1985, 87, that period. And it goes for quite a long time. Now in this 2000, in this millennium, 2010, 15 onward, another evolvement has come, which is called the fabless model, where you find that the company is only taking the marketing and the design systems, and foundry is the only responsible for manufacturing. So they are now not responsible for manufacturing. The whole manpower and overhead is utilized for design. And here lies the catch, how Indians and we are in a position to take the responsibility and getting the opportunity of this model, the fabless model, where you may not need a foundry, but if you have all the design tools and the IP idea for that, you can actually design from any corner of your country and the world, and you can actually submit the chip to those delegated foundries. And each foundry have their process, the PDK tool. So you have to develop your chip based on their PDK tool. For example, most of my chips I develop from TSMC. So I got the TSMC PDK file for 65 nanometer and 180 nanometer, 130 nanometer, like that. So, and that this is the IP, this is the PDK file that belong to only that fab. So you have free access to them. If you write to them, you will get that PDK file for taping out your chip. Mind it that actual chip design, and most of in our country, and not only I found that mostly they don't use any standard PDK file. They are just example, they make it by SPICE model, but actual design we should be based on the realistic PDK file, which is available from those companies through Europractice. So from Europractice, you can get this, download that one. You have to make a non-disclosure agreements with them, and so that you can make access to the PDK file. But you need the tools. So tools like Cadence, Mentor Graphics, or your Synopsys CAD tools. Those tools are the most expensive one. But for university, the price is not even 1% of the actual cost. So suppose you have to have five license, you will get to around 25 lakhs, like that. But if you want to buy it for your industry, it will be a few crores. And it is hugely expensive. So we thought of that how to take care of that tool licensing in a government level. So let me share some of the policy decisions that we have taken up in our committee. So the fabless manufacturing model, we have the wafer supplier. So you have to give the wafer specs. Normally the wafer is, now we are mostly working on 8-inch and 12-inch. And some cases we are going for the 6-inch. And I think 2021, TSMC will go for even beyond. That is nearly 1.5 feet. So that is the biggest wafer they have ever produced in the world. So they are working on that. So it is 18-inch. So that has not yet come, but they say that when break-even will start, they will go for 18-inch wafer. So we actually being there in Taiwan, and we hold that wafer just like a huge big 18-inch plate. We are just, and it's very thick, And normally the thickness of the wafer is for 8 inches, 675 micron. And then this, you have to give that. So if you are the customer will give you the specifications. Then device design IP, the process technology, high voltage testing know-how, product qualification know-how, these all belong to you. That is the fabless entrepreneurs or academia should now take care of this application knowledge, product definition, design support, and customer relations. So where you belong to this place, where you can make. And the silicon, then you will provide as a delivery the design and the process to the silicon foundry in terms of the mask file. We call it mask file. This is the mask file. So it is in a GDS2 format. And then you will get that silicon wafer. And you can then actually test it, verify it. And if there is a two kind of modes people are working in VLSI. One is short range loop and other is the final loop. Short range means within 3 months, you just send your design to get some idea whether things are working or not. And there is a long range means final things, which will be productized. Then you need a longer loop cycle. And longer loop means it takes around 9 to 12 months. So look at here for your concept, for pen and to get the chip tested out, normally you take around 12 months to 18 months. So while you are taking any challenge of making a chip, the VLSI, then you require actually an 18-month cycles, 12 to 18-month cycles. More you will be expertise, more will be enriched with experience of doing these things. Then you can reduce that cycle time. Even it will be 9 months. So normally every 6 months you will get a shuttle. We call it shuttle. Shuttle means that you have to launch your design on that shuttle. For example, yesterday there was a shuttle from TSMC at 180 nanometer process. This whole 1 year calendar will be given to you in the month of December. Then from January to December, you know that what technology and which day is the shuttle date. Accordingly, you have to plan your design and your student so that they should be able to send your design within that time, specified time. You cannot miss that time shut. And after this, they call it cold start. That means they will actually emulate your design in their platform and see if everything is correct or not. There will be thousands of errors. Don't worry about it. They will actually explain you all the errors. Then you have to solve those errors. Even after all kind of error taking steps like DRC clean and LDV clean and everything clean, but still while you will be emulating the actual platform, you will find a lot of errors that is coming. They will communicate with you and then edit your design a bit and send it. So it will take an 1 month window. So from the shuttle date, there is a cold start, we call it. There is a 1 month window. And after that, you will be able to submit your chip. For example, yesterday on 23rd, there is a shuttle for 180. So we have taped out, we have sent our GDS2 file yesterday, and we got a mail that they are now evaluating that, and then will be getting it, getting the results. Okay, so last say 10 years, so from our lab, we have taped out roughly 120 chips. So, and every year, we are, from my group actually, at least 3 to 4 chips are taped out every year. So I will talk all about that how to plan and how to proceed and how to make your design cycle much less time so that you can keep up with the time. And there is this next one is the assembly house, is where is the packaging part. So the packaging part is not the responsibility of the foundry. When I go to the actual example, there are a lot of packaging options you have, but you have to choose your packaging and bonding beforehand. When you want to work with high frequency design, then the design your design should incorporate the package model as well as the your bond pad. All the models, parasitic extraction should be made beforehand. So packaging is the most important part. You might be able to make your design in a die, but whenever it is packaged, there may not be a chip to get any signals out because the parasitic capacitance of that has grounded your signals. So please be that you should know about the packaging much before you start your design. Okay, and also the bond pad informations. And those informations, normally they don't want to give you. They will give you some vendor's name, then you have to talk with the vendors and so on. So this is the scenario. I think you have understood this. So we are in this domain. So we are in this domain, right? Our responsibility. This is your industrial responsibility. and this is the customer, and these are the fabless model, okay? And where you can, a process technology IP. So process people, those are working on the device using, say, Centauras or Silvaco, they will be working in this domain, especially for beyond 5 nanometer, when you talk about FinFET, gate-all-around kind of a device, or you can think about the double gate structure, a lot of various device structures, they will technology, this is their IP. Then device design. So these two, and then you can go for the testing and the IP for design and so on. So now come to this, the fabless model, why it is advantageous? Because it is low cost, don't have to reinvent the wheel, and mature manufacturing and quality system. Because if you think of the TSMC foundry, they are so mature that their tools are, I just make it rest assured before you send your chip. Because when you make the post-silicon, post-layout simulation, then if all the corners you have satisfactorily made these simulations, then I found that the actual silicon data, when you get the silicon and test it, simulated data not even vary 1%. So that is the strength of those foundry. That is what is your simulation. I'm not talking about the schematic. Schematic is not even I don't consider it as a design. Most of the people in India, they are happy with the schematic, but please believe me, it is not even 10% of your design. 90% design will come in the layout time. So layout will take 3 to 4 months, and continuously you have to evolve that layout and make the final the specifications or evaluations by post-layout simulations. If it works, then you're sure that it will work in the silicon, even with 1% variations in the all process corner. So this is the thing, and that. So if we look at from the IDM integrated device manufacturing and fabless, then we are in the design house, and this design house, this intellectual property or IP, where we can share. And that is the where it is the growth. And I will talk about what is at the moment the market, and where is the opportunity, and what is India's approach to help all academicians and industry people. So if you look at here, 2015, the market, Indian fabless market was $14.5 billion. Whereas in 2020, this year, the market goes to $52.58 billion. So it will be $80 billion by another 5 years. And where the cumulative accumulated growth ratio is 29.4%. So think of it, that how many people we actually require for IP generations for the design. We need thousands of designers, and there is not many people actually a good designer. There may be 1,000 designers in digital, there may be few hundred designers in analog, but there may not be few tens of designers in RF circuits. So that is the situation in today's things, that we don't have huge number of designers, because most of the institute doesn't have the access to those tools, to those PDK file, and also the required faculty. When I go for selecting any faculty positions in IITs and NITs, I do not find many students applied from the VLSI domain, because they are the most coveted people, and industry giving at least 2 times salary what IIT and NITs will provide you. So they are just, even the students coming out from my lab are 6 months before they are all booked by all these companies, before they submit their chip. So that is the market scenario of today's scenario in India, especially. I'm talking especially on India, okay? That there is absolutely dearth of people in the VLSI design. So there is no point of getting any sort of misconceptions that VLSI domain is saturating. It's not that, it's more and more it is coming because of the CAGR, you think of it 30%. And then the fabless model. So now you understand that we need that kind of a ecosystems have already arrived. And in this effort of ecosystems, MIT has given a very interesting, recognize these facts and very interesting approach road, which you should know as a member of that committee. Some of these interesting things that the build India as a preferred destination for fabless design. The enabling ease of business for startups and global MNCs. There are 67,000 IT houses only registered in Bangalore. After that, Pune, then Hyderabad and Noida. And out of that IT industry, the cutting edge technology in this, those are working, I call silicon industry. They are fabless. They are at least there are 400 to 500 entities in across our country. And only Bangalore, there are 250 startups. So even your students can make a startup with the IP, whatever they have developed, and they can actually start their own. And sometimes even the industry spin off their startup to reduce overhead costs, so that like cosmic semiconductors, okay, the high silicon, those companies are basically startup from say like company like TI. The TI then 4 or 5 senior design engineers, they think of it, why not we start something with our own. So they make their startup, and now they are so much big. You know that one company is sold to even this company, the Synopsys. Even one of my students who is working with IMEC Belgium, he also totally supported by IMEC Belgium. They have made a startup, and that startup, then I have actually insisted, why not you make the startup in Kolkata? So I am very happy to show that he has made that startup in Kolkata, in Salt Lake, Sector 5. So this is the way that how startup has come up in this our incubations in this VLSI design. So it is the enable tenfold growth in India fabless design. And at least we need $500 million company, at least every 5 years, at least 10 such company, MSME will come up. That is the kind of future model we have. I'm just going very quickly to give you the scope, because the main, the focus of this workshop is to let you know about the scope of VLSI. Then I say that at least 10 fabless MSME with 50 million US dollar per year to grow. And out of that, if you look at the market, this is for the regular and also for the defense and all. So you have a huge customer for that. And at least 100 MSME they would like to support. Means medium scale industry. Now this, how they will go into that model. So there is a market opportunity. So you will be getting a seed funding. Once you get that market assurance and people's skills, where academia can take it, marketing people will look at that. Then EDA tools for startups, EDA tools for MSM, and emulation rapid prototyping infrastructures. That is for rapid prototyping. And as you know that there is few things that when you talk about VLSI, then now in beyond move domain, VLSI standalone is not at all anything. It stands with a complete solution. A complete solution means it involves also the addition of or all the functionalities like analog, mixed signal, digital, RF together in a single die. Not only there, functionality integration, but also integrate with the sensing part and also integrating with the high voltage part. So that is the final goal. So one goal, suppose x-axis is that integration of various functionality, and y-axis is the node size. You are reducing the node size year by year. So now we have to take the resultant directions. So in resultant direction is that more than more concepts. That how to go beyond more is that integration, where you need this kind of a rapid prototyping infrastructures. CPU IP, because you know that now what has come up from India is Shakti, and government of India is looking for people, that is academic faculty or students, who can take the challenge of making a complete system using that Shakti processor. So there is a call in MIT. You can look at their website and find it out. So you can send a proposals to make a use of that Shakti CPU, the processor, to make an embedded systems, or to make a complete systems. For example, a complete transceiver systems using that. Then we need assembly of test and manufacturing and packaging. So there will be few center of excellence where the testing will be carried out. Now, if you look at the support structure, this is the most important part for all of you. All of you should know about that. Why I am saying so much of enthusiasm about VLSI. So if you look at the base of the pyramid, where we are all belonging to this part. So what is our impediments? Our impediments is that we do not have a high cost tool. So what we are thinking that to provide the virtual tool in the cloud. So you will be given with the license key to download, or the software will be with you to download the license key and make your design. And so that you can access thousands of designers, including industry, small industry, startup, as well as in academia. So the whole concepts of buying tools, we like to get rid of that. On the other hand, we want to make the whole tools, say thousands of license will be floating in the cloud, and once you register, then they will provide you that. So that is the first kind of help we are thinking. The government is thinking to provide to those colleges, industry, as well as small scale industry and startup. Then there will be some kind of R&D grant. Okay, so that R&D grant is called seed funding. And once you make a prototype, that is your product phase support, then you can call for a venture. There are a lot of venture funding available. So you have to convince them. After that, you can also go for a soft loan from Technology Development Board or Nidhi. There are several programs from there, and then the market interventions. So that is the pyramid. And as you know that the qualification threshold, as we go up, will be more and more. Lower side, the qualification, so that is stringency is less. But if you want to go up to the top of the pyramid, when you actually marketing your product, then actually there is a very stringent threshold for that. And that is the point where R&D grant and the virtual tool, that will be incubation zone. After that, you have to accelerate your work, your startup venture, and then you have to ultimately intervene the markets. So that is the fabless support structures, the model that we are thinking in India, and it has already been planned. I think from 2021, we are preparing the complete the policy and how the tools will be given to the cloud and how many. We are now calculating that one. So if you have any questions, you can ask me. I don't like to have a monologue. So, hello, is there any questions?
Yes, a small question regarding this venture tool. And these type of thousands of licenses, these are not prepared till now. These are under preparation. This concept.
Yeah, actually, what we are thinking, the phase 3 of SMDP would be like that.
Okay.
And the ministry thinks that it should start from January 2021. Unfortunately, because of the because of the COVID and all this, it is being delayed. And we thought of actually start along with our phase 2. Secretary said that why don't you start even 3 months or 6 months ahead of the second phase. So the second phase will be eventually it will be over by 31st March 2021. But our new phase will start. So, but I am not very sure about the present pandemic situations. It will be delayed because the final national level meeting has not yet come. So it will. We are now drafting. We are giving our feedback from various industry and academia and various nodal centers. You know that there are 6 and 7 nodal centers across across our country. IIT Kharagpur is one of them, and that is from there we are giving the ideas and our main thing. So that is the answers to that. So I think anytime in 2021 you are expecting this kind of a cloud where participants will be not only the academia but also startups and small scale industry. And you know that this academia would require just the hardware platform, and if they can draw the license key from the cloud, they can run a class, they can run a design, and it will be more accessible to more number of people. And one of the IIT will be the center for keeping those clouds server, actually the main, and another IIT will be the center for the hardware management, the total chip tape out, and that is to outside foundry to make a seamless operation, and testing and characterizations will be carried out by another nodal center. So that is the whole concepts actually coming up. But we are thinking of region wise because in eastern regions, IIT Kharagpur is the nodal center. Like in Western, IIT Bombay is the nodal center. South, IIT Chennai, IIT Delhi, and Siripillan. So like this, there are nodal centers. Now we have to decide upon that who will take the response. This is a humongous task to run such a huge activities. And so that is the answers to you that we are expecting by 2021. It should be by January.
We are also very much eager to have this phase 3 because I am.
Yeah, so for that you have to apply, and there will be some kind of a standard way of process of defending your projects.
Yes, you have discussed in detail.
So yeah, so I think all the participants, those are still listening these lectures, if they have any kind of a questions, he can ask me.
Okay.
Then I will start.
Any question, please, students and any faculty members of other colleges. Yes. So even the panelists of our colleges, universities.
Yeah. So that is
if you have any question, please ask, because we have the opportunity to have Torunda with us.
Yeah, yes. You can interrupt me at any point of time, and you should be able to. I am ready to give, because this kind of monologue sometimes very much boring. You know, better you should talk and give me some kind of a feedback, because I like questions. Okay.
Yes.
And if you look at the VLSI activities in my lab, in IIT Kharagpur, there are 22 faculty members involved in this lab. And there are 250 users at any point of time. Our lab is remotely, you can access, means within the campus definitely. Then the students and faculties, total 253 actually, 253. I look at the log sheet and find that all time these are busy. So our strength of this center is signal design. I think one of our students, Vibhu Shahu, he has given you just before me a talk, and he is also from the same institutes. He did his bachelor's BTech from IIT Kharagpur. Then RFIC is my area of the domain, radio frequency integrated circuits. Data conversion is Bihu is one of the key person in data conversions like ADC, DAC. Devices, I developed a small group there in devices. There are 4, 5, now 6 faculty members from EC departments involving in the devices. Then we have a big group in power management in electrical engineering group. And also there is another group, which is MEMS and interfacing electronics, which is my area of research, as well as a couple of other faculties from other departments. So this little old, 75 PhD, I think this has crossed at least 85 PhD and MS students have graduated. And I say that more than 120 chips have been fabricated from various foundry, not only TSMC, but also from National Semiconductors and also from the UMC and other foundry like IBM, those. And we have more than 20 patents, and even now it is more than 20 and 120 journals. Journals are even more than, I think, 200 already published from this lab. So in the VLSI, I'm talking only about the VLSI domain. And if you look at these, look at the distributions, so I feel the ENEC department at an instant time, ENEC has the highest login. After the electrical engineering, then AT disappeared. I am mostly interested about saying ATDC because even a biology or some other students working in, say, mechanical engineering, they can also handle with the VLSI design, especially in the MEMS part. So ATDC, there are, at any instant of time, I am finding 6 students working on it at any instant time. And computer science, from that, they are working 12 at that moment. And so this is the whole, this is, I think, long back we made it. So now it is increasing because of the pandemic. I think most of the people are working from the hostel. Those students are here or faculty members, but definitely now it is very less crowded compared to the real time during the actual when the system is completely on.
Excuse me.
Yeah, tell me.
Is there any facility you are thinking of that VPN, using that VPN?
No. Actually, no, we don't have any VPN kind of things because, as you know, that when you buy the tools or the license, there should be an agreement with the company, that is, for example, with the Cadence and IIT Kharagpur, and that and also the PDK file, you have signed an NDA with the Europractice, so that where being the head of that, so I have to sign on behalf of IIT Kharagpur, and their side they have signed, and as per that there should not be any abuse or misuse of that software tool. This cannot be used for any commercial purpose because they are giving us 1% of the total cost. So if you go for VPN, how do you know that it is not used for any company for their commercial purpose? So that's why VPN, we are giving within the campus, we are giving access to anybody, but outside the campus, it is almost none, because if it is caught, if anyone can download even a particular confidential file, then while we will print out, then a watermarking will come and my name will appear there. That is, I have no options to say I have not done this, because they can always track and they can report to you that this IP is not the IP which you have provided us, so it is an intruder. So you take care of that, and then we have to face a court trial in US.
Yes. So in that case, but
within the campus, within the campus, definitely you should have access to this lab. All the faculty members I have given access because I need the NDA with the faculty members. Those they sign, and the faculty members then on behalf of all the students of his, so they are giving that license key to all the students belonging to him. So this is the way how I work, because I am not able to control 250 entities, but I can manage 22 faculty members. So let these faculty members, and from that, so IP I am giving to the faculty computers, and faculty is now responsible to share that to any students. Then if something goes wrong, then I can catch that faculty members. So that is the way how I have planned it, okay? And so I have, so what is the facilities? Questions that might come up, that what is the facilities you require for an IC design and validations? So for example, you should have what we have at the moment: Cadence 40 licenses, Mentor Graphics 100 license, Synopsys 20 license, and Xilinx 10 license. And we can go up to 26.5 gigahertz testing facilities. I have made a state-of-the-art lab in collaboration with Keysight. Earlier it was named as Agilent. So all the testing facilities are available in my lab. So all the VLSI, including the digital, mixed signal, analog, and RF. So these are some of that, like noise figure analyzer, network analyzer, spectrum analyzer, high frequency, 50 gigahertz frequency oscilloscope. So all these are available in the lab, and also probe station. We have a wafer prober where we can actually probe the wafer, means in the die level before packaging. So this is the facilities a decent lab should have for actually to get. But if you don't have, if you have only the license file, then you have to contact the test, like IITs, where they have all the test facilities. You can check care of that. So this is actually the details of the EDA packages. So what are the packages you require? I faced these questions many a times. That VAC, these are university bundle. So you have to take care of that, what bundles you are buying. Because once you sign the documents and get your things, then you may not be able to run something which you require. So add something, then it will be very expensive. So you have to be careful about what are the to make the complete design. And for Mentor Graphics, what are the bundles you can get it? For Synopsys, what is the bundle you should buy? And for the Xilinx, what is the Vivado SDoc? So these are all the package which you require for your lab. Now I am coming to the most important block, which is the most how I actually run this lab. 250. What kind of hardware setup you require actually. So what we have done, we have two high-powered server. One is it is I think Dell, and this is an NFS server, and that server can go up to 5 GB RAM, and this is both are the same, but this is mirroring, you know, that if one fails, then other will work. Then I have a 15 terabyte usable. Actually, it is 18 terabyte. You can take 20 terabyte, but 5 terabyte is the system software. So you cannot handle that. So 15 terabyte is actually available for our working. And then there is a network switch. And then there are hundreds of such terminals across the campus. So this is the whole server client architectures what we have in IT. It is the biggest in India as far as the academic concerns, that we can cater to the need of hundreds of such client through this server. This is a very high-end server. So it costs...
This VLSI lab architecture that you are taking from the main, it is the central server, that from there your workstation, these are two?
VLSI lab have their own server. Actually, I have two powerful server. Each cost me around 26 lakhs. So it is 52 lakhs only for the server. Then I have all the terminals, so it costs me around 2 crores to make this whole setup without the tool cost. And if you look at the tool cost, the cost is unbelievable cost. So that is supported by the ministry. So this I cannot say. This is the whole tool cost is 25 crores. So if I cannot have that money. So that money will be supported by the government as a nodal center. So the actual cost of the tool, hundreds of license means pretty expensive. That is why we are thinking of giving it to the cloud, so that each one can have the license key as per their requirements. Some institute may not require 20. They can always spare the license to the neighboring institutes. So if it is a cloud structure, then I know your engagement model, and then we can actually share the licenses, because license is very, very expensive. Very expensive, the licenses. So it is total this SMDP is a 200 crore projects. You know, all over the nations, the total 200 crores, I think more than 200 crores is being utilized for to build that.
Actually,
So
hello, one point here, that when someone is like that, you are telling that cloud-based license, they are not actually cloud-based. They are setting up in a server from and the students or faculty member, those who are using, they have that not only the MAC address they have to give, so that they can only that faculty members or the students, those who are only that attribute in the computer, even they cannot enter in different mobile form or different computer also. So that kind of I saw it in the Cadence Entipple program. They have done this by accessing the server license, but through VPN, I can enter into their server. That is by viewing the viewer, VN viewer, and fortified client. By using that, we can access from their server. That I have seen. That is also a kind of networking and architecture that they have been using. But it is somewhat slow, and maybe if there are very good internet connectivity. And
so the kind of network what we are thinking is this one. So here you have a seamless, hundreds of terminals are.
Yes.
And they are connected to the server. And I have two parallel servers. So if one of them fails, automatically it is a mirror of that.
Yes.
So you will not find that any server is down or not. And you are actually getting the license key. You can also make your all softwares, okay, all the tools download in your computer. Suppose computer science department, they have downloaded all the software tools, but the license key they are drawing. So my server is not overloaded. So it is pretty fast in the lab. In what we have in our lab is very, very fast. So I actually given this model to my team. I showed it and they appreciate it. So I hope that this kind of environment will be created to avoid any kind of a latency. So latency should be less as possible. So seamless operations with say number of licenses. Licenses will be fixed. For example, NIT Durgapur. So we have given them say 10 licenses or like that. So that licenses will be, numbers will be fixed. Out of that license, you have to manage you. For example, we have 20 licenses, but you know, all the modules are not used all the time. 20 people, some people are working in one module, some people, so this way we can manage. Actually, we have 40 licenses and another 40 we have from our institute. So we have 80 licenses. So we don't have problem of licenses. So that is why I am saying that you need to make a proper, that is the planning stage, how this cloud server will work and how we can provide you the seamless operations who are the registers or the selected institute, industry as well as the startup. So let me come to the some of the activities going on to this lab. I am not going to the deep 5 years before or 6 years before. What I am doing right now. So right now, For example, all of you know that serialize or deserialize, SerDes, and all your USB connect have a SerDes. So you have, if you look at the IoT, in IoT you will have the thousands of sensors, billions of data that is coming in parallel, and then you have to transmit that one. While transmitting, how do you transmit? Through your optical backbone. So that optical fiber, before optical fiber, if you look at the RF over fiber, then you need the various kind of sensors. From there, you are actually accumulating the data. And these data all are coming in parallel. And there you need some kind of a serializer. And that serializer will actually serialize the data. And then by proper shifting of the voltage to electrical signal to optical signal, it will transmit it to the high GB kind of say 10 Gbps, 20 Gbps. Even now people thinking about 120 Gbps kind of a link. So where they will actually serialize the data. So always remember that you need to transmit your data. Before that, you require a serializer. And the opposite is also true, that you are getting a serialized data. Then you should be synchronous with your serializer. Then you have to deserialize that one. That means you have to make it parallel as per the source, sync with the source, and then it will be distributed. That is to your receiver side. So that is one such very important work that has been carried out for quite a long time. A couple of my PhD students have completed their PhD and still we are working on it. And if you look at that, what is the very uniqueness of that? The uniqueness of that there is not even any company who will give you a serializer, deserializer of 10 to 12.5 Gbps beyond, okay? Because only TI is manufacturing, or they have in their product library or product code only 10 Gbps serializer, deserializer. Just think of it, you have an USB where the data will be transmitted in 10 Gbps. So you don't need any time to store the data from your hard disk with a pen drive. So that is the kind of speed we are thinking. And but people are thinking now to go even 120 Gbps because of the terahertz and all kind of thing. And they are working with 7 nanometer process. So we are now also working with that company to develop that one. So that is and you know, this is the 10 to 12 Gbps. It is even hardly available in commercial level. So, and these are called the strategic devices. So you may not get access to this. They will not quote you actually. So anything 2 to 4 Gbps people will get. But if you want to go beyond 10 to 12 Gbps serializer, deserializers, you won't find that. So if you look at that, let me give you the overall architecture of that. Now, there are a few things. I will go to the actual board and explain you that there are parallel data, that is all the sources, right, for all the sensors. And that goes to the data select mask. And then there is a mask, and you can actually find that it finally goes to its serialized port. So this is parallel input and this is serial output. And where there is an internal clock generator by a PLL circuits. And you know that in this case, the clock is not we are not getting the clock from the source, but from the data we have to recover the clock. So one of the most important unit for that is that CDR. That is a so along with that, there are several such blocks, functional blocks. It is called a complete ASIC, complete system. Okay, it is not a simple component. There are actually 12 functional blocks inside to make a complete chip. And we have made it using 65 nanometer process from TSMC. Okay, So you understand that there is an inside a PLL reference clock generator. There are multiplexers serializing the data and then transmit it to fiber coupling. So from the electrical domain to optical domain, there is some kind of a conversion, and then finally it fed to the optical. And there is a 100 ohm impedance matching and all this matching networks. And the PLL is nothing but a frequency synthesizers where a lot of innovations have been out of that. So if you look at here, this is some of this the view of that layout. This is a VCO, this is a band gap reference. So you know that all this block should be given with the voltages. So you need to have a band gap reference and a power management circuit so that nothing is loaded. So you have to make those very carefully, and as well as there are few things that how to isolate various blocks from the power shortage. So if one block is gone, so other blocks should not be affected. So in the layout, I will give you more in the layout after some time. But very interestingly, actually, you can make those things. As a professional designers, you have to take. And how to test it? Then the chip has a PRP as
Hello.
a pseudo-random sequence generator. Let me
Sorry
finish.
to interrupt you, sir.
So this is a
Ma'am,
yeah,
we are limited to 6:15, so we have to close the session within 6:15.
Yeah.
Madhumita ma'am, sir, we have to go for another meetings at 6:20, sir. 20:25. Madhumita
I'll
ma'am,
finish
will-
it.
Torunda,
So-
okay,
Ma'am.
we can continue up to 6:15, no problem.
6:15. Okay.
6:10 by 6:10 we can
So
then discuss
this
5 minutes for question and
Yeah.
then
say now come to the various forms of this. Now you understand, you can look carefully, there is a bond wire connected to that. So you will require to have a bonding diagram, and also you have to make this is a full chip GDS. This is the finally you have to submit. So if you look at here, finally the board has been designed at IIT KGP, and you can make this kind of socket where your ASIC can be inserted. So you know that you have 20 such packaged chip. So if one chip doesn't work, or you have to check all the chip, you do not require 20 boards, because this is the main test board what you have designed. Okay, so you can use ORCAD or something to. This is working at more than 20 gigahertz. So it's a different kind of a board, and these are all test point. So you can actually make use of this test point and the fine tuning of that. And the board is, there is a socket. So you can buy a socket where you can actually place all the chips, say chip 1, chip 2, chip 3, chip 4, same chip, but you want to make some statistical variation. So, you know, I said that for any statistical variance, you need at least 20 die or 20 packet chip. So you have to give the mean variations, the median, and etc. to make it as a commercially successful product. Okay. So you not think of it that all the time you don't, these are leadless package, QFN leadless package. So you have to make some kind of wave soldering. So all the time you cannot do that, right? So you make a socket made for you, and you will just put it the chip 1, 2, 3, etc. and test it. Now this is the whole test setup you require. This is in the lab, the whole test setups of this, and there is an NXP controller, microcontroller board. You can program the whole microcontroller board using a PC, and then you can drive the inbuilt software into the systems, and then will start working. So you need a lot of power source, highly accurate mixed signal. This is, I'm talking about the mixed signal oscilloscope, arbitrary pulse generator. Internally, you have a PRPS. So all kind of supplies, then signal analyzer. So all these things you require to test that board. And then you find that what is your, this is whether your PLL is locked in or not. So I can found, you see that this ring oscillator provides me a fantastic oscillations at 2.4. This can vary from 2.45 to 6.34 gigahertz, with no other side or harmonics. So that is the beauty of that. And so you can look at here the results. So what I said that when you make your ASIC, then you should have all the test structures and the pins out of that. So each of the components of this functional block, you can test it independently. So that, for example, I am designing a frequency synthesizer. The frequency synthesizer might have the charge pump, the filters, the PFD, the phase frequency detector, the divider, and the VCO. So, and if you just say I have one output from the VCO, that will give me the no. This should not be. So you have to test individually your charge pump. You have to test individually your the filter circuits, the divider circuits, and the VCO. So you have to make test pin, and each test pin should not be loaded with the external device. So when you actually load it with the oscilloscope probe, they have their parasitic capacitance. So that capacitance will add and it will give you a distorted signals. So to avoid it, what you have to do that, you have to buffer that one. So you need a lot of buffers. So try to make the buffer, which is basically a source follower, unity gain buffer, and so that you can have isolations from the output load to this side to the chip side, so that your output node from the chip is not affected with the loading at the test sites. So you need a buffer. Don't forget all this. So first is segmentations of test pins, then definition of various test structures, then putting buffer to isolate the pin and the output. So that is few things, hard rules for making a ASIC, making an ASIC. Now the most important point is known as this is called the I. So if you look at the bit error rate of your data recovered after the serializations, so then you have to check the bit error rate. As the bit error rate is more, you will find the I is less opened. And if you look at the width of that, so that is the definition of jitter. So you can find it, and that is post-layout simulations. You have to play with the post-layout simulations. Even 1 picosecond delay you have to compensate. So mind it that when you talk about the tens of hundreds gigahertz kind of a serializer, deserializer, data bit rate, then you cannot afford to even miss 1 picosecond delay. So your layout should be extremely careful. You have to be careful about that. So this is what we are now going into the 20 Gbps serializer, deserializer in our next run. So we taped out 2 chips, 12.5 Gbps, and there is no substitutes in India, and the even better than the TI, they have specs of 10 Gbps. And so this is some of the very interesting ideas that how we are working with a complete system. A complete system. Before that, I am just going to show you some, because you are not in the lab. So let me give you a live performance of the lab. You just hold for a minute, and that will give you a very interesting idea about what we are doing.
Yes, we are waiting.
I just you can find that one very easily from the YouTube, but can you see that?
Yes.
You can see, right? 1 minute.
No. That video is not showing. Your
Video is not showing?
No, till now not.
What you are seeing?
Yes, the video is not playing. You have to open the video from the next application.
What I can do?
Sir, sharing button.
Share.
In the
Just 1
sharing,
second.
the video will
Yeah,
be
I
available.
am going
Yes.
to the actual demonstration of that
Yes,
work.
sir, you have to click on that video. Yes, sir.
So I have to click that video. I am clicking it and share.
Sir, yes, sir.
So is it visible?
No, sir. No, sir. You just do one thing, sir. You just stop the sharing right now, and
What I can do
reshare
now?
and choose. So you close the stream now. Stop sharing.
There is a share, right? Oh, this is not that sharing.
Yes, sir.
So Zoom sharing.
Stop.
Yeah,
Yes, sir.
stop.
Now, sir, you share.
Share screen. Yeah.
So click on the video that is displayed
Yeah,
in
click
the
on the video.
application.
Right.
Yes, yes. Then at the bottom there is share.
Yeah. Now you can see.
So now it is, yes, sir. Yes, it is coming.
Yeah. So
Yes.
just you wait.
Yes, it is coming.
So please, I am starting that.
Sir,
No,
do you want to
sound is
Yeah.
sound also?
sound is not coming.
Do you have to give the sound also, sir? Hello?
Yeah, 1 minute. Sound I am giving.
Sir,
But it is
sound,
in
no, sir, sound is
Bengali.
not coming. So sound
Okay,
it is
no
not coming. You
problem.
have to
Yeah.
just
No
reshare,
problem.
sir.
I am just explaining this. So just
Okay,
you are
sir.
seeing the test setup.
Yes, continue, sir.
So can you hear?
No
No, sir,
sound.
sound is not coming,
So
sir.
what
So
I am
you have
trying to
reach
say
there.
that
Yes, sir.
what is the purpose of a serializer deserializer, and I am showing you the online measurements, the live measurements. You can see the eye diagram of the data. That is, the data is received at the oscilloscope, and you can see that setup. Now I will show you how the chips look like. You just follow that video. So synchronously retrieve the data. So deserializes means you have to again parallel the data. Say you are receiving the data at 2.4 gigahertz, then suppose 4 such lines, then it is around 10 gigahertz, then you are so serializer deserializer, right?
Trying to take a photo.
So we are talking about the clock source, how to make that clock source and all. So I am just making it little faster. Yeah, you can see the board.
Yes, it is.
These are,
Showing.
you can see the board.
Yes, sir.
Yeah, I am
Yes,
talking
it is
about
visible.
the socket, right? So on the socket, we put our ASIC. Yes. So this is the chip. The inside the hole, there is a chip. Yeah,
Yes,
yeah.
it is visible.
So this is all the M connectors. If you look at, these are all M connectors. Okay, forward we are connecting it to the whole board is designed at IIT Kharagpur, including the chip. But the chip is 65 nanometer, which is, yeah, so that is the input out. We are defining the input output pins. Yeah. So this kind of test board is required for any ASIC design. Yeah. So these are all the SMA connectors. And if you look at the board carefully, the board, these are electrical trace. So that traces are actually made by ADS software. So since at high frequency, you require some EM solver so that impedance is matched. Okay, so it is SARDIS IIT KGP. Now look at the die. So if you look at the 65 nanometer die, so these are the die. Okay, so I will ask him. Yeah, he will show you the dies. So it is 7 millimeter by 7 millimeter. The whole system has been done. Yes, so now you can see, you have seen the packaged one. Now you can see the die. This small die, this is the 7 by 5 millimeter SARDIS, where the complete 12.5 Gbps serializer deserializers has been designed. And you have to be very careful about handling that one. So you can look at the packaging. Yeah, this is the packaging. So this is leadless QFN package. This is 48 pen leadless package. Yeah, and this is the actually you're seeing the optical microscopic view of the chip. So when you make the layout, you have made the layout. Then you, when the die will come, then you have to actually take the die for with your layout. It is the only top layer is seen. Yeah, you can see. So I am seeing one inductor there. Okay. So you think more you are expanding, you will get thousands of such components in and around. Okay. So it takes nearly 1.5 years to design it. Yeah. So it is purely online. So the data is coming and we are checking the bit error rate. We are checking the jitter and all the things. Yeah. So, you know, this is the computer where we have programmed it. And then this is the emulator. And then we are finally giving to the PCB. Because you have to program your chip according to your instruction set. This is the cable you require for high frequency measurements. So this is the random data which is coming from the receiver side. So this eye diagram is the most important for looking at the data transmission, whether there is a bit error is coming or not. Okay. So this is called unit interval of the bit. So you have to sample at the middle and there is some range of sampling. Anyway, so this is the, so next one, before I start the MEMS work, let me give you a bird's eye view of my lab of the where the MEMS microfabrication. So this is also another video you can find where I have explained the things carefully. In the lab, you require a clean room for that. So if you think of it, so this is a 2-inch wafer, silicon wafer. What is happening? So think of it, how the evolution of the silicon technology. So it's a double-side polished silicon wafer. So 2-inch wafer is converted to 3-inch wafer. So after that you have a 4-inch wafer, okay? And one side cut means this is P-type. If it is cut is depending upon the cut, you have to find out. Yeah. 4-inch and if you look at that machine, it is the diffusion furnace. All of you know about how to diffuse boron, phosphorus. So you need a furnace for that. So this is the loading one. I will show you the loading. How to load the silicon wafer and to oxidize the silicon wafer. So where your process recipes have to be fed into this, there are 3 such furnaces, one for phosphorus, one for boron, and another for oxidations, okay? So now I will show you the loading. So this is the elephant. This is made of quartz. Yeah, you can see that when the furnace is around 900 to 1100 degrees centigrades, then through that elephant, which is a 3-zone furnace. So at this, it is a 3-zone furnace. In the middle of it, we are actually, So wafer is being fed to the furnace at say 10, 50, 100, and after the oxidations, we take out the wafer. In this carousel, you can actually make 25 such wafer. Okay, you can go up to 4-inch wafer. So you can first step for any MEMS process or any microfabrication, including VLSI, is the oxidations. Then I showed you oxidation. Then you require some kind of sputtering. So this is called a RF magnet on sputtering unit, DC sputtering unit. So where you can sputter oxide, nitride, or any metal inside, and this is designed by us. So here we have actually make one plasma chamber. This is all human machine interface, and this is the computer for lab view, and this is the total chamber, sputtering chamber. So all the gas lines are on the walls. So you require argon for the sputtering gas, and rest of the gases are actually there are 4 gases. If you want oxygen, you can throw oxygen, etc. Now there is a special chamber we built. It is called plasma cleaning chamber. So when the wafer, this is called translator. When the wafer is fed to the system, then you need to clean it a bit in that chamber, then fed to the main chamber. Main chamber is around 10 to the power -7 milliwatt, is the base vacuum pressure. So what you understand, for depositing oxide or nitride, one is the diffusion process that I have showed, that is by the furnace. So if you look at the history of that, this is 40 years old diffusion furnace, where all the units are bits and pieces that they are assembled, right? But when you actually have seen that diffusion furnace is fully automated state of the art. So 40 years, how the technology has evolved. So same 3-zone furnace, but here you have this bubbler, you have those the flow controllers, you have those switches. So all bits and pieces. So you can have a feeling of doing some experimental work, but why in the automated system, then you will be less actually accustomed to inside. It is totally computer programming, and then you require normally for diffusion furnace for around 6 to 9 hours, depending upon how thick you require. So there is a warming cycle of, there is a total diffusion process, so another 3 to 4 hours, depending upon the thickness, and another 3 hours. So this is DRI. So once your pattern is placed on the wafer, then you need the fluorine chemistry to etch the silicon to make the device. For example, MEMS devices. So this is by plasma etching. There are two plasma sources. One is called ECR plasma and other one is RF plasma. This plasma is etching dense plasma, basically the fluorine ions that etches the silicon. Okay. So this is a computer robotic hand where you have to put your wafer, and then a robot hand will come from the main chamber and it will take out the device or the wafer inside the plasma chamber for etching. So mainly once you etch the DRI, you need fluorine chemistry. It is carbon tetrafluoride or silicon tetrafluoride. Those kind of gases are used. Those gases are pretty toxic in nature. So you need some carrier gas like argon or dry nitrogen to flow along with that. Normally argon is used, and there are few things are added. How do you know that your etching is over? There is an endpoint detection. There is a lot of other techniques, spectroscopy, the plasma spectroscopy, where you can see which species are coming out. So all these things. And this is an electron which is used for multi-layer metal targets. As you know that in VLSI or MEMS, you require metal interconnects. So that interconnect should be of ohmic in nature. So you need those kind of metal interconnects. There is also a plasma cleaner, and after that you have to put it to the electron beam evaporators so that the routing or the metallizations can be done layer by layer. So there are 8 such metal can be actually patterned or can be deposited one by one by these techniques. So this is known as the E-beam techniques. Now coming to the another most important process for, so for example, you have seen that, right? You have seen that in post layout, but how the layout is being made in a, so we need actually one laser writer. So this is the laser writer which actually translate that GDS2 file, that pattern which you have seen in the computer 1 second before, and that is actually on a photoresist coated glass, or this is actually the glass is sometimes the chrome coated. The laser will directly write on silicon or on the mother wafer, and the typical resolutions of this laser writer is around 0.8 micron. So you can make your all pattern. I am not talking about 65 nanometers. After that, once you make, then this is called photoresist spinner. So wafer is now sucked in a vacuum chuck. Then you actually pour photoresist, positive or negative. Then it is rotating at a speed of 45,000 or 4,500 RPM or 6,000 RPM, which determines the thickness of the photoresist as well as the uniformity of that. Okay, so this is called the spinner. So this is the next step. So when you spin it, you can see that how the photoresist coated silicon wafer is seen. Okay, then you actually, these are single-sided, these are double-sided mask aligners where the silicon is placed okay, the photoresist coated silicon, and then on the top you have to make the mask, and then by UV exposures you can actually transfer the pattern of the mask as per your GDS2 file on the silicon wafer. And once it is done, these wafers, then what you will be doing, you will be actually then etch it with the DRI orbit or wet chemical thing. So now it is okay. So this is the whole thing. This is a single-sided mask aligners. And in case of double-sided mask aligner, you can actually give this is the double-sided. So both the uh, both the sides can be actually patterned aligned with that. So this is how the a total view of how to how a MEMS fabrication lab looks like. And let me, because give you, now I am going back to my original PPT.
Thank you, Torunda, for showing us this video. It is looking like live. But I have visited several times your lab, and during the time of Vidhan was there at that time.
Yeah, so can you see the
NTDC also? Yes.
Can you see the slide now?
Yes, yes, it is visible.
Yeah, visible. So let me see. Yeah, so let me just explain you that now what we are doing with all the institutes I am coordinating at the moment. So we are trying to develop a early warning system for earthquake detections. That means there will be an accelerometer. The accelerometer will actually sense the seismic events. And just 1 minute. I don't know that some sign is coming. Anyway, so I don't like to waste time. Yeah, so now if you look at here, there will be n number of such sensor actually placed at the hilly terrains of Sikkim, and they will even now we are making the sensor subsystem, the MEMS sensors. This is the front end, and then the ADC, then the DSP, and this part is called the front end part. And then if you look at the this is NIT Sikkim and the IIT Kharagpur, this phase 2 program, and this is analog front end. It is made by NIT Durgapur and IIT Kharagpur. ADC is by IIST and DSP by IIT. So this way we have segmented our whole work in different institutes to make an ecosystem so everybody learn and share their knowledge each other to make a complete early warning systems for your for the earthquake detections. So this is how we are doing it. So there are few chips we have already developed. This is the full diagram. I mentioned that the VGA chip. So very recently we have made this chip. Just yesterday we have taped out that one, which is a complete frequency synthesizer with the front end as well as several oscillators together. So if this is at 180 nanometer standard TSMC process. So if you reduce that one, let me, my God. if I want to reduce that one, then I can give you a very interesting concepts about, yeah. So now you can see that this is your whole chips. The many chips are there, many test structures, frequency synthesizers, or many other things are there. And these are the external pads, okay? And all this, there are 16 pins each side. So there are actually how many? 64 pins chips, and that is the whole die. That is 1 millimeter into 1 millimeter die area. The whole system has been incorporated in it. So this is by TSMC process, and we just taped out yesterday in the evening. So I am giving you latest our work, and which the oscillator can work at 2 to 6 gigahertz for any kind of transceiver design, which is where you want to have the local oscillator frequency. You can find that kind of chips. So this is we are expecting within 3 months this will come. So with this, I like to thank all of you that I have given you the what is VLSI and what are the scopes and what are the prospects of that professions and how the chips are built, what are the various process, what are the supports you require, and also showcased you some of the work carried out from my group as an examples. So if you have any questions, you can ask me.
Okay, actually, we are running late, Turunda. So in that case, I think if there is any question, please give on the chat. And before completing the session, I want to thank again, because of this elaborate the scopes that we can have in future from different government policies, and even that the IIT KGP, what they're thinking in future, so that every institutions can get get help and be motivated to do something. And yes, it is a good venture that you are doing so many things. So one question, Turunda, that the power that you are giving to this chip are coming from where? It is the power inbuilt, that battery or like that, or any system separate power you are providing there?
Sorry, I can't see you. What is happening? I don't know. So yeah, what is that power is the power, you need the power from outside, but you know that we are, can you hear me?
Yes, yes, yes,
Yeah,
I can hear.
so, yeah, but I cannot see any of you. And also I cannot see that Zoom part. So where it has gone, I have no idea.
So
Anyway,
at the bottom in the taskbar, you can find it, sir.
task, there is nothing coming.
Yes, sir, there is some Zoom menu.
Zoom is there. Zoom is there.
Below taskbar, you have to open.
There is nothing.
Yeah, just
angle
click
button,
on
sir.
the menu.
So at the bottom taskbar.
There is no nothing. No bottom taskbar. Yeah,
Okay,
there
sir,
is
okay, sir.
something. Yeah. Now can you see?
Yes. Sir.
Yes, yes.
Yeah, yeah.
Yes, sir, yes,
So
sir.
now you can actually ask me questions because I am completely, yeah.
Yes.
Yeah. What
One
is your
thing
question?
that work has been completed, the part they are contributing in different way, the different institutes. The part in phase 2 that is in SMDP.
Yeah, the idea. Yeah, that part. Everybody has their work carried out because you know that we took the responsibility of mentoring them. Whole design was mentored by us, our team, and delivered. Then we have actually designed for them, showed them how to design. So this is a 5 years projects, and it is going to be aimed by November 2020. But it is, I think, extended because of the COVID. It will go up to 31st of March 2021. And this is the approach that how to make a complete system
Yes.
where the other institutes can also learn how to make chips and how to make complete systems. So this is my experience, is that some of them, like any class, you will find good students and mediocre students, and some of them not very interested. Also, I find while coordinating the overall activity in national level, I find that some of them are very enthusiastic. For few, I don't like to name any universities. Some institutes have even taped out more than 2 chips, and some even very reputed universities not able to deliver any chip till now. But they are still learning, and actually depends upon the interest of the PI and interest of the students and their motivations. Mostly the students, they are more interested about machine learning, deep learning, all kind of things now is the buzzword. But they do not know that actually India is now going towards the VLSI revolution, and we need billions of dollars business coming up, and thousands of engineers required for VLSI design, and that is the core engineering sectors. It's not that you have to do something for banking softwares or social science, but most of the students. So my part is to tell all people that there is abundant opportunities, especially in VLSI design, both in digital, analog, mixed signals, and RF. And there is no dearth of opportunities and the organizations there. Don't talk about always the big industry. There are a lot of small startups, small MSME. They are hiring people and they are giving good amount of salary. So like that, so students in classes, various kinds of students. So while I am coordinating the activities, I found various approaches from the work, but it is more or less we have been able to finish all the work. That is the beauty of these coordinations. And suppose ADC is analog A to D converter being mentored by us, and it is actually developed by IIST Shibpur. Taped out 1 chips, but they taped out more than 2 chips of different reconfigurable A to D converter. So I think that way they are quite strong in VLSI design. NIT Durgapur in the variable gain instrumentation amplifier, they want to make something. They have recently, because you know that 180 nanometer you can also do it in SCL process. So I give that once you have not much confidence on making the chip, then we'll provide you the SCL foundry, which is free, which is not free because you don't have to pay. But for the TSMC, you have to pay a lot. So you have to be careful about spending money before you are not sure that your chip design will work. So that I give them, okay, let you design something and submit it to SCL. And then if it works fine, then you can also work with the TSMC process, which is the state of the art. So that is the way I found that there are very enthusiasms amongst the various universities, and they taped out chips. And they yeah, please, if you have any questions, you can ask me.
Thank you, Torun. Actually, as we are really we want to involve in this kind of, because we have microelectronics and VLSI design, both are there. So and Kharagpur IIT and your advice we will be getting even more often. And the students of computer science, IoT and IoT branch and IT, more departments. So the number of departments are growing more and more, and we have so many affiliated colleges, so we can make a strong group also if you can guide us in a proper way. So we are ready to accept it, and the next phase we want to join in your program. So if you can in within this time, what a shorter problem that I am thinking on, that the power backup and the battery management, if you are have already been done, then that we can contribute, but we can think on, because we are already got a DST project on solar power management, solar installation actually, and
Yeah.
there we are trying to MPPT controller and other system. There also we are trying to.
So what I am suggesting you that the power group, we have a designated power management group
Okay.
which is led by Professor Amit Patro of
Okay.
Electrical Engineering Department. There are 4 faculty members. Amit
Okay.
Patro, then Devashish Mondol, who is my PhD student. Another one is, there are 4 faculty members, but Amit Patro is the leader of that. So you should contact with them if you have anything related to the power management or high power circuits design and all. But we are involving with the low power design and power handling of across for ASIC, where the power consumption is within few milliwatts of power. So because you know that we have to make our own BGR, the band gap references, which will be temperature compensated, and process corner variation should be as less as possible. Even you can make current control driver. So because you have noticed that I have not gone into design of any particular VLSI circuit. In spite of that, I make use of that forum to let you know that, let people know about what is VLSI and where it is moving, what are the opportunities coming and the scopes, and also giving you try to give you an hand-holding experience of what is VLSI design and what is microfabrications and all. So in spite of going into a particular topic of designing something, I have actually purposefully not gone into that because I made it only for people, or especially the faculty members, to make aware of this kind of activities and how to give some kind of a feeling that what they want and how to build up the VLSI or microelectronics activities in their institutes, and how to motivate their students and how to actually start working. So if the purpose of my lecture for last 1.5 hour is like that only.
Okay.
So just
yes, we have got that, and I'm telling about that for this phase only, but we are interested in different way, IoT based and integration of that you are telling. We are interested in different way, and we have a very strong personalities in Professor Sinha, who is very like experienced in handling digital VLSI system and design, and we are
Sorry
we
to
have
interrupt you,
a
ma'am. We
device
have to
also.
close the meeting, ma'am.
Yes, thanking you once again, Tarunda. We would like to have another lectures and near future also.
Yeah, so then probably any other lectures where I can give more details about the design aspects. But all this, the videos, it is documented by by Doordarshan, so you can find it. Just type the microelectronics and IIT Kharagpur. So that is a 1 hour documents on my research work. You can